You want me to start?
Well, I think we're live, so let's say hello to people. I can sort of introduce this.
Okay, go ahead. It's your show.
Right. So for people who are joining us, we have been having working sessions talking about our physics project for a little while. Today we are starting a new and different kind of working session, which is talking to outside folk and trying to learn from them about things they've been doing and how they might be relevant or not to our physics project. Maybe other people finding out things about our physics project too. Today, for our very first of these, we're pleased to have Jim Gates, who actually, I guess we first met like 40 years ago.
That's correct, Jonathan, at Caltech.
Yeah, right. So it's and you were already doing supersymmetry, is that right, at that time?
That is correct. That's where we wrote our book on superspace that has sort of become a standard in the field.
Oh, that's the 1001 something. What's it? What's
the 1001 lessons on supersymmetry. That's exactly right.
Okay. So now you've been working on. So okay, here's well, maybe you want to say some things to introduce yourself, or maybe we can.
Sure. So as Stephen mentioned, I've known him since 1980. I was a postdoc at Caltech. And I was there along with a colleague of mine named Warren Siegel, and we were working on something called supergravity, and this is like in 1982.
When that was a very unpopular topic.
That's right. Most people thought we were kind of crazy. In fact, I wrote MIT's first thesis on supersymmetry, and when I did that at MIT, I was the only person in the entire institution that knew anything about supersymmetry. So it was kind of a peculiar situation. One of the interesting things is I met John Schwartz. And came out to Caltech in 1979. And we started working on a problem. And I was there for like a month. We didn't solve the problem. This problem has never been solved in the field of supersymmetry. So the thing that I'm doing now, Stephen, is in fact trying to finish my homework from 40 years ago and figure out why we couldn't solve this one problem. And nobody in the world has solved it. It's quite remarkable.
So you and me both are working on homework from 40 years ago. But so tell me what is that problem?
So can we share screen now so I can put
Sure.
Okay, so
let's go ahead.
Let's stop the video and do a screen share. And here we go. Let me come on the side over here. I prepared some notes from this. As you can see, there's a familiar name there on the side. Is everybody seeing my desktop?
Yes, lots of points of files. Great.
Yeah. So this is a primer on supersymmetry. So let me talk about that first. If you look at all the particles in the standard model, this is what we see in nature. We have a set of particles that we call force carriers. They are all bosons. That means they don't obey the Pauli exclusion principle, as you well know, Steve, because you started out as a particle physicist. I remember. Yeah, right. When you were in school at Caltech. But all of the matter particles are fermions obeying the Pauli exclusion principle. So you look at this table, and if you see most displays of elementary particles, they're nice and symmetrical. You'll notice this is not. And the reason is because I've classified them by whether they are force carriers, which is the top row, or whether they are objects that the forces are exerted upon. And then I classify them, do they obey the Pauli exclusion principle, and they don't. And as you can see, it's a crazy table when you look at it like this. It's so crazy you might think something is missing. And so you might think the world could look like this. This is supersymmetry.
So what are the current, I don't follow these things in great detail, but the efforts to find these supersymmetric partner particles, which people were sort of hoping the LHC would be successful at and so on, how far away do they have to be consistent with current experiments?
So I think so. The LHC, which has now ended its second scientific run, has put a lower bound on masses like this that is something like between, say, 14 and 20 TeV. We know that these things do not have masses less than those numbers.
So let me ask you a question about that. I'm sorry to jump into particle physics.
No problem, please. This is a conversation.
So, back in the day, actually, when I was at Caltech, I did this thing with David Politzer, where we were looking at, how the Higgs particle gives mass to particles. And what one of the things that happened there, when you try to have a very high mass particle like a fermion, for example, with a Higgs provided mass, the second order corrections in the effective potential cause the cause one to have this instability in the Higgs as a result of the Higgs mechanism. How is that avoided for supersymmetric particles?
So it turns out that in supersymmetrical systems, you're exactly right. It's a great question. But in supersymmetrical systems, the vacuums tend to be more stable than in non-supersymmetrical systems. And so that's part of the, so there's kind of a built-in damping process. So we can push that number much, much higher than you would if you were just having non-supersymmetrical systems. Basically,
so in other words, the Higgs coupling, the fact that there's a high Higgs coupling, which leads to a big negative term in the effective potential when you have a fermion loop there, is somehow, the fact that that's there is somehow because you're canceling it off from the boson terms or something?
That's exactly the mechanism. Basically, you're looking at vacuum fluctuations, and so they damp it out, and so you can get away with a lot more if you want to think of it that way.
But you still have to pair up. I mean, if you have a 20 TeV fermion, it's kind of got to be paired up with an order 20 TeV boson to cancel that term.
Exactly correct. When you get to energies, let's say close to the Planck scale, where essentially all masses will be negligible. But even, you don't even have to go that high. But you're right. The pairing in masses at high energy scales, you expect the spectrum to be equal. And this is what, yeah.
Go ahead. So I'm curious. Okay, let me ask some basic questions here, because
sure.
We're trying to understand in our models, for example, we're trying to understand how particles emerge in general in our models. We understand something about how localized structures can exist in these hypergraphs and so on, but we haven't yet gotten fermions versus bosons.
Right.
So, I'll ask the following question. So, a defining feature of a fermion is that, it's a spinor representation. It has, when you sort of rotate by 360 degrees, you get a minus sign,
yes,
etc. In your setup, I mean, the fact that we only have fermions and bosons, and we don't have, we have whatever Z2 graded algebras and things. The fact that we don't have things with weird parastatistics.
Right.
Is that obvious why that should be always the case, or is that something?
It is not so obvious, although, let's just say, if you make the assumption that only Z2 gradings are possible, what you find is that this is compatible with lots of extraordinary mathematics that you would think is not connected with this at all. So, for example, in the way, and we're going to come to that later in this talk, I'll talk about
right.
Take care of that Z2 grading. But if you follow the arc of our research, say for the last 10 years, you'll find things like because of this Z2 grading, we ultimately are able to get to Calabi-Yau manifolds, even though this is not string theory we're talking about. Riemann surfaces make their appearance. A number of just stunning mathematical results result from this Z2 grading. So we think there's something very special about it.
But could I as well have, I mean, if I had, fermions, bosons, it's either +1 or -1, could I have some other, fifth root of
Sure. In fact, those are called, as you mentioned earlier, parastatistics. As you probably recall, Stephen, I spent 33 years at the University of Maryland. I'm currently at Brown University. But at University of Maryland, one of the world's experts on parastatistics, in some ways the father, a physicist by the name of Wally Greenberg.
I remember that. Yeah, right.
Yeah.
Before QCD and color before it was clear that when you had three up quarks in a delta plus plus or something particle, it wasn't clear how that could possibly work with the exclusion principle. And I guess that was invented.
That's exactly right. And so Wally's one of the people who said, maybe there's another kind of statistics at work here. And so he's an expert in that. And so he actually, in the early 2000s, was actually proposing experiments that I think some were actually done at NIST. You didn't need colliders to do these experiments to look for this parity violation sort of effect, and nothing was found. But the mathematics he had explored and developed to an extraordinary degree.
But so just to understand, if we are looking for particles in our system, and remember, we don't have, and we're going to talk about this at length, we don't have fixed dimensional space. We're dealing with this network, which can have an effective dimension that can be even fractional and so on. So my question is the fact that in our 3+1 dimensional space-time of traditional quantum field theory, is the fact that we have fermions and bosons and not some parastatistics thing something that is in any way related to that dimensionality, or is it something where, oh, you could have, parastatistics with a permutation group of, I don't know, however many elements or something?
Well, as I said, mathematically, from the work of Wally, we know that mathematically there's not anything that forbids that from happening. The fact that we haven't seen it may have something to do. My intuition is that I think it may have something to do with Lorentz representations, which you brought up earlier. And also, since you brought up networks, in the scheme that we're going to talk about, which is this set of objects we call Adinkras, networks are, in fact, our starting point. Although they're not the kind of networks clearly that you're working on, but they are networks. Yeah. Okay,
so I wanted they're related to irreducible representations. Is that correct?
Yeah, that's correct.
Okay, so I wanted we should you've clearly got a few more slides here, and I think that would be.
I do indeed.
Okay, so let's. And it looks like Boris here was also on our chat and was maybe we should just introduce. We have at least two other people here. We have Jonathan Gorard, and somebody with you, Jim, Boris, who
yes, Boris was actually my former student. I taught him quantum field theory.
Okay.
So let me just finish this, and then we can start getting into that.
Yeah. Okay.
So,
great.
So I'm going to talk about the problem that John Schwartz invited me to come out to Caltech to solve. It's this problem. If you look, you can see there's some operators. I call them D alpha and D beta, and then there's a factor of 2. And this thing called sigma is basically a gamma matrix. And so the question is, what in arbitrary spacetimes, what are the irreducible solutions to this equation? And believe it or not, if you don't impose dynamics, no one has ever been able to answer this question. And this was the question that in 1979, within the context of something called N=4 super Yang-Mills theory, this is the question I tried to answer with John Schwartz. And we couldn't find an answer after a month, and no one has ever found the answer to this question.
Okay, so let me understand what this equation is.
Sure.
So what are these D's on the left covariant derivatives of some kind, or are
they are in fact what is often referred to as supercharges. They are the generators, and we're going to talk about this in great detail later, but these are the generators of supersymmetry transformations. They are the things that change bosons into fermions and vice versa. Okay,
so there's an anti-commutator of those guys equaling, and what's that partial derivative on the right?
That's a space-time derivative. That index that you can think of as d mu in more conventional notation. So it has a spatial part, which is the d0 component, and then it has d1, which is the x derivative, d2, which is the y derivative, and d3, which is the z derivative. Or in general, if you were in an arbitrary dimensional space, like say M theory, where there are 11 dimensions, then that d partial derivative must run over all directions.
Right. Okay, but so let me just understand on the supercharges on the left.
Yes.
These are supercharges enter a Lagrangian, for example, as it's like a charge multiplied by the field operator. Is that right?
If you want to talk about some property of a fermion, but the basic idea is let's talk about SU3, which is something we all know. In SU3, we normally represent the generators by matrices, and we represent the states by little column vectors. And you let the matrices act on the column vectors, and then they move the entries of the column vectors around. So in that setup of SU3, the so-called Gelman matrices play the role of the Ds here. They're the things that cause the motions of the representations that you're talking about. These are
so we got a matrix. Okay, so let's just set some. So we're trying to get a matrix representation of this presumably super.
Sort of. We don't really want matrices for the Ds because, as you well know, because I remember your thesis among other places, as you well know, there are some operators that don't have finite matrix representation. So we're not really going to be after a matrix representation. I refer to SU3 only as an analogy so that people can begin to understand why we look at equations like this.
Okay, but roughly, oh, wait a minute. So the representations you're interested in are some infinite dimensional representations. Is that the idea?
Yes, that is correct. They're fields over space-time and therefore infinite dimensional.
Okay. And so just to give me an analogy there, I mean, if we're looking at the standard Lorentz group and things, is there what I mean, where where that decomposes into in 3+1 dimensional space-time, we've got an SO3 or SU2 type thing.
That's correct.
Representing the spatial degrees of freedom. What is the analogous thing here?
The closest thing here are actually the momentum generators. As you also well know, and when we write p mu in quantum mechanics, if you try to write it as on a representation, that turns into a partial derivative with respect to x. And so these things are more akin to the translation operators. In fact, these things are called super translations.
Okay. Okay. So I still haven't quite wrapped my head around what is going on in this equation. Actually, I'm going to ask Jonathan, since Jonathan didn't say anything yet, and Jonathan's always good at decoding notations of things. Jonathan, do you understand what's going on here?
I think so, but I do have a couple of questions. So
okay, Jonathan,
is it reasonable just to think of these D's as being just odd generators in a super Lie algebra
as translations, as odd translations in a super algebra?
Okay, so they specifically have to be translations.
Yes.
Okay. Okay. And these and the representations you're talking about, even if they're not finite dimensional matrix representations, do they still have to be sort of linear endomorphisms of some kind, or can they be somehow more general?
That's a correct statement.
Okay, right. So you can't go to something more general like a D module or something.
No, not general for these.
Okay, fair enough.
Good.
Yeah. Okay, fair enough. I think that makes sense. If they're just so all the odd symmetry generators of a super Lie algebra can be considered super translations. Is that right?
The ones that are connected to space-time supersymmetry. If you talk to mathematicians, they have a whole general class of super algebras that have nothing to do with space-time translations. But the ones that physicists use, the answer to your question is yes.
Okay. Okay. I didn't realize that was a restriction. That makes sense. Okay.
Yeah. Okay.
I think I see what this means.
So this is space-time supersymmetry, not super. Mathematicians have a much broader category of things they call super algebras. We are not talking about that broad category. We're just talking about things where the d mu on the right-hand side of the equation is a space-time translation generator. And we're going to talk about, so to see how these things get realized, as you said, Stephen, you really want to know what they do on a representation. So I'm going to talk about that shortly. So, but the point is, this equation, no one knows the answer to. So, I left Caltech in I guess it was probably the spring of '79, extraordinarily disappointed that John Schwartz and I had not been able to solve this one problem. And this problem has actually never been solved in over 40 years. So in the 90s, when I was already a tenured full professor and I had an endowed chair, when you get that kind of freedom, you can start doing research even if other people tell you it's impossible to solve problems. So I decided in the 90s that I was going to go back and try to understand why we were not able to solve this problem. And
actually,
so,
just to help people, including me, let's zoom out from this problem and ask, why do we care about this particular problem?
So imagine, we earlier, Stephen, and I know you studied this when you were a graduate student, so I remember sort of watching you. Let's talk about SU3 for a moment. Suppose someone came along and said, okay, I've heard about these things called quarks. And you say, okay, fine, I know about quarks. And then they said, I can form bound states of these quarks. And you say, okay, I can find bound states. And then they ask, well, what are the representations of these bound states? And then, so example, it becomes a problem a little bit like adding spin, right? If we have single spins, there's spin up or spin down. But if you have a bound state of 2 spins, you have 3 states that are irreducible representation and 1 singlet state. Or if you had 3 spins, then it starts breaking up in a more complicated manner. So that's the question we're trying to solve for this algebra.
So one thing I don't understand about that, in the case of SU3, going, the interpretation of SU3 in terms of quarks doesn't have, there are no spatial derivatives involved there.
That's correct. That's one of the fundamentally different things about supersymmetry. That's exactly right, Jonathan.
Yeah. Okay. So let's go back here. So let me understand that. I mean, so you're saying, if I was just dealing with SU3 and I was just trying to find the multiplet structure of SU3 with random bound quarks and things like this. I mean, actually, okay. Actually, let me ask even a more naive question. Okay, so in your supersymmetric models, is there an interpretation? Are there spinor-like things like the quarks of SU3?
Yes, there are.
Okay, and so but you are trying to find a multiplet structure for this like 11-dimensional whatever it is.
M theory, it's called.
Right, but that multiplet structure is not one that you think you can interpret in terms of just sort of combinations of fundamental particles. Is that true?
That's correct. The representations themselves, how do I say this, have to be mathematically independent functions. They won't be dependent on anything else. So they can only depend on space and time. They can have different spins, but that's all we allow.
But so, I mean, back in the days of SU3, you know, when SU3 was originally being formulated in the early 1960s, you know, people like Murray Gell-Mann, you know, thought of it initially in a purely mathematical way with just,
Yeah.
you know, and then it was only later that it became clear that the, you know, spinor representation of SU3 or whatever it is could actually be represented, you know, there were just quarks and you could just say, how do the quarks add up? And that's how you get protons and so on.
Correct.
So the thing I'm trying to understand here is when you're looking at these representations of these super algebras, I guess.
Yes.
The interpretation of that, I mean, okay, I'm sorry, to back up a bit. I mean, when we're looking at the Lorentz, at the Poincare group, for example, for space-time symmetries,
yes.
and we talk about the representations of that, and we say, oh, the various spins of particles come out as the different representations of that.
Yes.
That we're not imagining that a spin 3/2 particle is made from a combination of, you know, 3 spin-1/2 particles.
That's correct. It's an independent representation.
Right. So in other words, it's a different type of thing. In the case of SU3, or, you know, so-called constituent SU3 or whatever, it was eventually there was an interpretation in terms of more fundamental particles.
Right.
In the case of something like the Lorentz group, there isn't. There's just a, you know, these are the possible representations. So these are the possible spins that can exist. And so
that's exactly right.
Okay. So then what you're doing is something
is more
analogous to that second case.
That is exactly right. That's what we're after.
Okay.
Now you wanted to ask about representation. I'm going to show you the simplest representation. Let me first of all back up because I'm going to cheat. So the problem that that no one in the world has solved is this problem up here that I'm pointing to with my cursor for arbitrary dimensions. So, you know, 11 dimensions for M theory, string theory in 10 dimensions. But for arbitrary number of space-time dimensions, you want to solve what are the representation of these equations if you make no assumptions about dynamics.
Yep.
No one knows how to solve that. After over 40 years, no one has ever solved that problem. And that's the problem that John Schwartz and I failed to solve in 1979 when I was visiting Caltech for the first time. So in the middle 90s, I said, okay, well, if I can't solve this problem that I'm pointing to, maybe I can solve a simpler problem. Namely, let's go to imagine a world where there's only a temporal dimension. Mm-hmm. And yet you have these operators that can act on. So in a one-dimensional world with temporal dimensions, all the fields are just functions of time. Let's call it time. They're just functions of time. And so let's imagine that you have operators like this, but in this lower dimension. So I kind of switch notation slightly. And since I only have a time derivative, then the algebra above could only look like the thing I'm pointing at with my cursor now. Namely, the anti-commutator of these supercharges in one dimension have the same normalization. In one dimension, the only thing that I don't have any sigma matrix, any gamma. All I can have is a Kronecker delta and a time derivative. So this is the analog of that algebra, but in one dimension.
Okay. And
here it turns out I can solve the representation problem because here's a representation. The quantity, so I introduced some number of bosons. Remember when we looked at the standard model, we saw all the Higgs particle and the force carriers. So I introduced some number of bosons. I call them phi I with a lowercase Latin index, and some number of fermions. These are like the quarks that we saw in the standard model. And so I asked myself, on this representation, can I realize that algebra that I wrote? And the answer turns out to be yes. And now what you can see is that here I can actually classify the representations if I can classify the matrices that satisfy these conditions.
Okay. And the hat on the indices is something to do with
the hat okay, so this it's a subtlety. Thank you for asking. So I had to introduce some number of bosons. I'm pointing at those bosons with my cursor. I have to introduce some number of fermions. I'm pointing at the fermions with my cursor. But the number of bosons, so in general, you could ask, suppose the number of bosons, which is index I counts, is different from the number of fermion, which the number k hat counts. So that's all we're doing. We're using a notation where, in principle, we're asking, could you have unequal numbers of bosons and still have supersymmetry?
Okay.
Okay? So that's all this notation is doing. And now, if you actually So how do we figure that out? Well, you'll notice that this is a first order differential equation. That's a first order differential equation. Let me hit this with the second one of these D's. So then on this side, it's second order, but then using this equation, I just have a D hitting on psi, so it becomes first order, and I can concatenate. I can do that with the indices in different orders, and what that does is put a condition on these numerical matrices that I introduced claiming I was hunting for representation.
Yep.
Those two conditions are what you see below.
Right. So, okay, so you can presumably solve those for matrices of certain dimensions.
Exactly. So in one dimension, the classification problem turns out to be relatively trivial. Namely, if I can classify all sets of matrices that satisfy these conditions, I have found all, at least a starting point for all representations for a supersymmetry.
It looks like Boris here has a question. That's what was, we should let Boris ask his question.
Thank you. So D's also contain gauge fields, right?
No. These are just operators. Let me try to find an example. If you'll give me a second, let me try to find an example of what I'm talking about here. And since we're all on internet, you can do this along with me. Namely, go online to your browser. And I'm about to pull mine up here. Oops, that's a, let me open a different window. That's just a message from Danielle. And you can go to, perhaps to Spires, right? You know how to get to Spires, Boris?
Yes.
Okay, so I'm going to do the same thing. Inspire, and the word.
Boy, it's amazing. Spires was the preprint system at Stanford that existed when I got involved in particle physics back in 1975.
Exactly, and it's only evolved just moderately.
Okay, has it still got a command line interface?
Yeah. Exactly.
Right. Okay. Good.
Okay. So Boris, for your benefit. So here's the Spires link. Click the Spires link.
Yes, I am. Right. It's a new Spire. Inspire.
Yeah, the front end is new, but it's basically the same old function.
Right.
And now type in find a gates and.
You probably want find with a D.
Well, you don't need the D. It turns out.
Oh, okay. Okay.
That it knows not to.
In my case, it remembers your name because I searched it recently.
Okay, so these are papers that I've written with my graduate students, and they're here. I hope they're online too, because they're the one. If we get into talking about Mathematica, Stephen, I'm going to get my graduate students involved. Okay.
All right.
Okay. So let me go backwards. I don't want that one. Let me just do another find, namely find a gates and just mock. So here we have a list of some of my recent publications. So let's go back in time to this one. So this is a paper I wrote with Hazel, who presumably is online with us. And we're going to go and just get that preprint and click on the PDF.
I have never heard of holoraumy. Maybe I'm about to learn what that is.
That's one of my. It's a joke. I'll tell you.
Oh, okay, you invented that term. All right, I don't feel quite so bad then.
It's a joke. No, it's a joke. So the reason I got this paper is because this whole discussion. I'm sorry. This whole discussion about.
I got that.
Okay, so this is a discussion about SU3. So I'm going to try to use it to explain some things about supersymmetry. In SU3, in the abstract, there are these objects that you can call the generators. They're just one half of the Pauli matrices if you go to a specific representation. But as someone who does mathematics, you can just say, gee, there's just a set of linear operators.
But those are not the actual Pauli matrices. For SU2, they'd be the Pauli matrices. For SU3, that's something different.
For SU3, they are the lambda matrices, the Gelman matrices.
Right.
So you would just, but in the abstract, you say, gee, there are these operators and they're linear and they satisfy some condition. And this is the condition where some of these coefficients F are non-vanishing that you can see here. And if you pick these coefficients, these are the generators of SU3. So when you saw on the previous slide, when I had the D's, you should think of the D's as playing the exact same role as the T's in this equation. Is that okay, Boris?
Yes, now I see it right. But then there is no sort of a dynamics between fermions, so to speak. Yeah, there is
right, because in SU3 you don't need fermions to talk about SU3. It's a classical Lie algebra. It has nothing to do with fermions.
Let me just understand something, because the thing I really want to push on later is talking about how you reconstruct, given a knowledge of representations, how you reconstruct the group from them. And I guess here, if I throw you I mean, those structure constants, the Fij,
Right.
Are characterized, those can be computed from the Lie algebra, yes?
Correct.
And there's a certain set of possible combinations of those things that represent the possible, Lie groups and so on.
And it's classified by Cartan.
Indeed, right, with nice Dinkin diagrams and all those kinds
exactly.
of
In fact,
things,
it's funny
right.
you should say Dinkin diagrams because I was going to go there next.
Right. Okay, but that's nice. Okay, so wait. You've got nice pictures there.
Well, that's why I went to this paper, Stephen, because we got all this stuff
fine.
here. Okay, so let's go back a little bit. So here we are back at the matrices.
Right.
And so if you choose to let the T's be matrices, the T's can act on column vectors. Those are the things that provide the representation. And so you can ask, well, gee, if I take these T's and act on these column vectors, what do they do? But if you take T3 and T8, as you well know, these are the ones that define the eigenvalues. They're diagonal, and so you just get relationships that look like this.
Boy, I learned this stuff when I was a kid. So what, T3 is isospin, T8 is hypercharge or something, or did I get it wrong?
You got it exactly right, Stephen. Your memory's still good.
Okay, good. But that's okay. And then down there you have an anti-commutator, and those are
because it turns out that if you choose these T's to be matrices, no one says you have to take the difference in the product. You could take the sum.
Mm-hmm.
And if you do that, it turns out you get a different set of objects that are not the structure constants. They're called the D coefficients. In old-fashioned strong physics, these things used to be used to describe interactions for strongly interacting particles.
Right.
And in fact, if you do the calculations, I've actually worked out for you here, what are the specific non-vanishing values of the D coefficients. So the first thing in thinking about supersymmetry is always in the back of your mind to have this picture of how classical Lie algebras work.
Mm-hmm.
Okay. So I'm gonna put this away for now because we may come back and use it some more. Let's just put it away.
Sorry, can I ask a very naive question?
Sure, Jonathan.
Okay, I'm trying to get a better intuition for the question that Stephen asked earlier about why, in good old-fashioned SU3, you don't get space derivatives appearing.
That's correct.
But you do in supersymmetry. And I'm trying to get some sense. Okay.
So
one way to think
of it, Jonathan, is that it's a definition. In other words, if you were going to do SU3, you wouldn't stop with just T1 and T2 and T3. You get all eight of the T's if you're doing SU3, right?
Right.
Okay, so it turns out in supersymmetry, if you just take the things with the D alphas that I wrote, that does not form a closed superalgebra. It's just like in SU3, if someone said, I want to just take, say, T1 and T5, right? If you took T1 and T5 in SU3 and took the commutators, you would find on the other side something new.
Mm-hmm.
And so then you would take that something new and say, okay, I'll take T1, T5, and this new thing, check the commutator algebra. You would then start to generate new things every time until you got to all 8 T's.
Mm-hmm.
And at that point, you calculate the commutator. I don't ever get anything new from taking the commutator.
Right.
And so the point is that in supersymmetry, if you start off with these D's, they don't close by themselves. You have to include the space-time derivatives for closure of the algebra.
So what would that look like? What would the analogous thing look like for the Lorentz group? Does the Lorentz group have that same kind of structure? Because
it does not. It does not. So in the Lorentz group, let me think for a second. Is there an easy way? Let's just go out online because Dr. Google is a wonderful thing. So let's just put in Lorentz group here, Lorentz group, and see what we can find out there. Actually, I had this diagram on my talk.
Use Wolfram Alpha.
No, we don't. This is not what we solve. We would solve we can probably tell you things about the Lorentz Group, but we don't solve giving you narrative about.
Okay, well, Jonathan, let me turn the screen over to you, and you find me some pictures of the Lorentz Group. Okay,
I can try.
No, I said, Jonathan, go to Wolfram Alpha and find me what the article on the Lorentz Group.
Which the.
Is Jonathan still there?
No, I don't think. I mean, we're not going to have anything terribly interesting, probably.
Oh, so I should go back to the boring.
I think you should go back to what you were finding. Right.
Sorry. So I did just quickly want to ask. So this closure that you need, or the space-time derivatives you have to add in order to get closure of the Lie algebra.
Correct.
Do they come
super Lie algebra?
Oh, sorry, of the super Lie algebra. Sorry. Do they come in? So presumably they don't come in at the level of the odd generators, because those, as far as I know, only introduce permutations and time derivatives of the superfield components, right? So they must come in at the level of the bosonic generator.
That's also correct.
Okay. So I mean, is there a nice geometrical way of thinking about like sort of why that happens? I mean, because they're just the bosonic generators are presumably just derivative operators acting on.
That's all they are, as I mentioned when we first wrote the algebra.
Okay.
But so physically, you're saying that the engagement of the super algebra with space-time happens through the bosonic degrees of freedom. Is that what I'm learning from this?
Well, you actually have to have both kinds of degrees of freedom. In order to have supersymmetry, you must have bosonic degrees of freedom and fermionic degrees of freedom.
Indeed.
Yeah. That's one of the defining features of that representation I showed you.
Absolutely, right.
But I mean, yeah, go ahead.
No, I'm just trying to understand. As you're saying, the Lie algebra does not close unless you have these space derivatives.
That is correct.
But you're saying that the fermionic degrees of freedom somehow aren't the ones that have to pull in. I mean, because the spatial, well, here, to be very naive, I mean, the spatial degrees of freedom, the spatial derivatives don't have, I mean, they're not Grassmann-like things, are they?
No,
I mean,
they're
just regular derivatives that have, that work the same way that have, as opposed to being some kind of fermionic degrees of freedom.
Correct.
Okay.
So the message is, if you want to do supersymmetry, you've got to be committed this is part of that Z2 grading that you were asking about.
Yeah.
So
Okay.
you have to admit the Z2 grading at the first step in some sense.
So let's see. To derail just a little bit, because I'm really curious about. I mean, one of the things that, well, maybe I think you were still explaining the representation problem that you're trying to solve. But then I at some point I want to jump in and ask a bunch of things about.
This is a freewheeling discussion, so I don't mind at all.
Okay, all right. So let me launch into the thing that I guess I'm most curious about right now.
Okay, go right ahead.
So we have. I mean, I could perhaps show you. If you stop sharing, I could just bring up.
You want to take the screen? Okay, I'm going to put my stuff on the side here. Go ahead.
All right, let me share here. Okay. Oops, that is sharing. Figure out. There we go. Okay. So, I mean, what we have in our whole setup is, we have this whole notion of the spatial hypergraph.
Mm-hmm.
And the way that, we imagine particles work in this is by having various kinds of sort of topologically stable structures that can maintain their identity as they propagate through space, basically. Okay, so for example, to understand the limit of this object, when it gets, the large scale limit of this object, we understand how to compute dimension, we understand how to compute curvature, we understand how to make geodesics, we understand how to make, we just starting to understand all kinds of other things you can make out of combinations of geodesics here, okay?
With you so far.
Okay, So here's the thing that we're sort of trying to understand: what is spin? We're trying to understand that that's something which we expect to emerge from features of the space-time structure. Then the other question is, how do local gauge groups work?
Yes.
And the way we think those work is when you do these underlying updates, there are in general many ways that the update can be done. So there isn't just one possible way to match the rule to the underlying hypergraph. And we think that the sort of the combination, the way that you can get combinations of those things will give you kind of the local gauge group. And to show you, let me show you one example of this, if I can pull it up. Let's see if I can pull this up. Here we go. Okay, so this is the thing where we are looking at the different ways in which you can do the different ways in which you can match the underlying hypergraph when you do an update. And there are different ways you can do that, and there are permutations that you can make of the underlying elements in the hypergraph. And depending on what rule you choose, you get different permutation groups that correspond to the sort of the freedom associated with how the update gets done.
Mm-hmm.
Okay, so the speculation is that the way you get local gauge invariance is by essentially a large-scale limit of this kind of ambiguity in the way the updates happen. And so one of the questions is, how do you take, so what we have here is something where we've got at sort of a local level, we're doing these updates on this hypergraph, and we have certain updates that are equivalent to other updates. So we can define permutations that say which different underlying elements can be exchanged with which underlying elements. So then one of the questions is, if we know a big bucket of permutations, we're looking at we're looking at sort of the rewritings of larger and larger chunks of hypergraph. And so we're defining certain rewritings are equivalent to certain other ones. So there's a certain collection of permutations that leave the rewrite invariant. Okay. And so we've got this collection of permutations. And so one of the questions is, how does a collection of permutations limit to a Lie group?
Yeah. You have an answer?
I have a partial answer, but I'm trying. That's one of the things I'm trying to figure out. And I'm trying to figure out. So, for example, in the case where our spatial hypergraph, so we can measure the dimension of the spatial hypergraph by looking at the growth rate of geodesic balls in it. So you start from a node in the spatial hypergraph, and you just keep looking at things which are increasingly higher radii away from that node. And if the growth rate of the geodesic ball, the leading term is r to the d, then d is your dimension. Mm-hmm. But that d doesn't necessarily have to be an integer. And so one question is, so I'm skipping around a little bit, and I'm going back to something more like the spin case. In that case, how do we understand the symmetry group associated with, so let's say we've got this thing, and we know that this network is limiting in some sense to a d-dimensional manifold. So we would expect that that thing would somehow have some kind of, if it's somehow homogeneous, isotropic, it would have some kind of SOD symmetry.
Right.
Okay, so the question is, what is SOD for non-integer d? How do we think about it? What and can we, for example, use representation theory to get sort of I mean, what we're looking at here, when we look at the space, and we're looking at how does this space limit to d-dimensional space, we've got this notion of we got these geodesic balls we can build and things like this. The thing I'm trying to understand is, what about the symmetries associated with this? How do we, can we, for example, just as we take limits, and there's an unformed thought, okay? So just as we take limits of this discrete spatial graph to correspond to a manifold, can we take limits of something which is determined, let's say, from permutations or something on this discrete graph, and that somehow can map into representations? And can we somehow take some limit of collections of representations to be the thing that will correspond to this, sort of continuous manifold that exists in the Lie group.
So let me ask you a question, Jonathan, because you sort of triggered a thought. That's not Stephen.
This is Stephen. So
I corrected myself, Stephen.
Right.
So you asked, what is SOD in non-integer dimensions?
Yes.
That's not a question I've ever thought about before. However, I do know that mathematicians have this notion of fractional derivatives, and that would seem to be the appropriate place to start to try to answer the question, because I would think that one could take the notion of fractional derivatives and see if you could write a set of generators for the rotations in terms of these fractional derivative operators. And whatever comes out of that, that's what I would expect to be the definition of SOD in non-integer dimensions.
Okay, so I'm slightly pessimistic about that.
Ooh.
Actually, it happens that our company, we have one of the sort of world experts on fractional calculus.
Okay.
Although I have not specifically asked him that question, it is my impression that the way essentially what you're doing in fractional calculus is, the standard formula, integral of x to the n, x to the n plus 1, over n plus 1. You're essentially generalizing that by something like an analytic continuation.
Right.
And I think, I might be wrong, but I don't know. I'm well. Let's just think about that for a second. In the you're saying that. Well, no, I don't get it, because when you go to SOD in d-dimensional space,
right,
you're not changing the order of the derivatives.
No. So look, maybe I'm wrong, but I would think that somehow trying to write the we often write the rotation generators as matrices. However, we also know that we can write them as a single power of x times a partial derivative operator, and then look at the algebra of that object. That's a vector field, right? It's a set of vector fields. Yep. And so if you're doing something that's fractional, I would have thought that, gee, maybe if I change the derivatives to be fractional derivatives, and I look at the algebra of the vector of this set of vector fields that limits to OD, then that would be the definition of what I meant by OD for non-integer D. That doesn't make any sense to you?
Yeah, I understand what you're saying, but this is why I'm not convinced about that. Okay,
I see.
So in the way of constructing with x dot derivative and things like that, it's still always, even if you're going to SO5, SO10, whatever you go to, you're still just using those same linear derivatives. You're not changing, right? So I don't think that the fractionality of the derivative is what's important. I think what you need is a fractionality. Let's say you have a matrix representation.
Yeah.
Okay. What you need is a fractional sized matrix. In other words, instead of an n by n matrix, you have to have an n fractional by n fractional matrix.
Yeah, half by half matrix. I understand. Yeah.
Right. And so a question would be, actually, now it makes me wonder. Okay, so my thought would be the representations are that they have an independent existence, independent of the matrices that happen to form, that happen to be able to be used to represent the representation, so to speak.
Sure.
So my thought would be, just looking at kind of the skeleton of the representation, is there a way, if somebody throws you, here are a bunch of representations, what group does this correspond to? How, you can answer that question. You can say, this is the collection, this is the stack of representations, this corresponds to the following Lie group. So what I'm asking is, maybe what one can do is to look at a different sequence of imagined representations, so to speak, or skeletons of representations, and say, what would that sequence of skeletons of representations look like if the limiting group to which it corresponds is, SO 2.5 or something.
Yeah. I understand what you're saying. I have, look, this is not something I ever thought about, but the calculational scheme that you're describing would be something I would expect. If you just carry out the calculations, you should have an answer, or at least your colleagues or whoever it is.
Well, let's see. But okay. So now I'm going to. Let's take. Okay, I'm going to ask naive questions, which maybe would be. Let's see. I think I had.
I have a question. Are we going to get back to supersymmetry?
Yes, we're going to get back to supersymmetry. I think supersymmetry, I'm hoping supersymmetry is relevant to this question.
We'll see. We'll do the best we can. Let's go.
Okay,
Sorry,
all right. So first question. What's that?
Just before we do, can I try and I'm trying to understand Jim's point about fractional derivatives. I'm wondering, okay, is what you're saying basically because the way you represent a sort of an infinitesimal rotation is obviously you take an identity matrix and you add a times some d theta for some vanishingly small d theta and some a in little SO3, right?
Yeah.
And so was your point that one way you can think of the fractional dimensional rotation matrix is as being an infinitesimal rotation, but where the d theta is some fractional operator?
That was my question.
Because I mean that doesn't seem as crazy as Stephen made it out to seem.
Okay, walk me through this,
I
Jonathan.
hope it's not crazy.
It seems like a sort of that's some sort of local Taylor expansion of dimension.
Yeah.
Okay, so what does the infinitesimal? So if I take this and I look at the thing with I look at an infinitesimal. I mean those are the coefficients of the d theta.
Yeah.
If I'm not mistaken, that will be the coefficients of. I'll take an identity matrix. So just to understand how this would work, I would take in this case, I would take a 2-dimensional 2x2 identity matrix, and I would add this matrix times d theta.
No, well, I would say take that operator and let the theta in that be a small parameter, and then keep only linear terms.
Okay, fine. Yes, but okay. So if I keep only linear terms, then that corresponds to this with theta goes to 0.
That's correct.
So okay, so fine. So what you're saying is what I should be looking at is that identity matrix plus, some d theta times this thing here.
No, Stephen, not really.
Okay.
So first of all, I would back you up and ask you to write the following. If I'm in a 2-dimensional space, I can write x times ddy, since you're going to be doing the x times the partial derivative with respect to y, minus y times the partial derivative of x, and that thing is a generator for the rotations on the 2-dimensional space with coordinates x and y.
Indeed.
Okay, right. Now if I change the definition of the operator d so that it is a fractional derivative,
yep,
then I would ask myself, so if I calculate this same object where the derivative is a fractional derivative operator, what happens on the other side? Or more generally, I would have, of course, different, I'd have d different coordinates, but this is just the simplest example of what I'm talking about.
But if I were to if I had a 3-dimensional, normally, if I go to a 3-dimensional rotation, I just have a slightly more complicated version of this.
Well, you have three copies of that, basically.
Right. But I'm not changing the d's in that case.
But you're not changing the d's.
No, but the question would be, if you looked at an operator d, d to the 1 minus alpha for some sufficiently small alpha, and then you applied it and you constructed a rotation matrix in that way, would the rotation matrix you get out act like a rotation matrix in n minus alpha dimensions, or maybe n minus 3 alpha?
I don't understand how you
get
a
question. That's right, Jonathan. That's part of the question I'm asking. If I change the definition of derivative, what happens to the notion of the generator of the? Because, like I said, I've never thought about this before. That's why this is an interesting conversation. But so if you have an expert who can answer that, that's what I'd ask them.
Right, I agree. That sounds like a plausible line of argument. That you may
so
be
one possibility is fractional derivatives. I mean, we sort of tried to think about that before and concluded that it wasn't promising. But just to ask this question about representations, because I think it's going to merge with the supersymmetry discussion. I might be wrong. But okay, so and now I'm being naive here because I don't remember but just the representations of SOD. If I just asked for the dimensions of the representations of SOD, or just for if I'm remembering correctly, for SO3, it's just things like 2n plus 1 or something is for successive. Am I right? Am I misremembering that?
No, but I can look those formulas up. I think what you're writing is just what's called the Cartan subgroup. I think you're writing the number of generations Cartan subgroup.
Okay, so but what I'm asking is, are the irreducible representations of a group, to what extent can you use them to kind of let's take a look here, see what we can find here. representation theory of SU2. I mean,
Can I mention one way in which I think Jim's idea is actually very interesting, which is that.
Thank you, Jonathan.
No, you're welcome.
Actually, I'm curious about the answer now that Stephen has pushed me this direction. I would be very curious to know if you take the operator that's on the screen and you extend it full to 3 dimensions, putting in the y and the z. The version. This is the x, y. You would have a y, z, and a z version of the. I'd be very curious to know what would happen if I took the definition of fractional derivatives and calculated the commutators of the things I'm talking about. I've never seen this anyplace in the mathematical literature, but it's a valid question, I think.
Right. So I was going to mention that the place where I've seen the most similar idea is in category theory. So that in category theory, the general notion of a representation is you have one object with a notion of a composition, and then you define a functor that maps it to a different object with a similar notion of composition. And if you then think about a group and its representation, the functor that maps the group to the representation is some generalized derivative functor. Go from the representation to the group back to the group is some generalized integral functor. And I'm wondering, because there is a notion of sort of fractional, as Stephen has kind of first made me aware of, there's this notion of fractional dimensional tensor products in category theory. There are these things called Deligne tensor categories. And I believe, although I'm not quite sure, that one way you can construct them is by having an integral functor that's effectively a fractional integral. So I'm wondering if you translate it from the kind of abstract categorical setting back into something concrete in terms of matrices, whether it actually does make sense to have fractional derivative operators and then consider kind of infinitesimal perturbations in the dimension.
Sure. So, like I said, I've never seen this or thought about it, but whoever your expert is on this sort of thing.
Yeah, well, I just asked whether we could find our 2 experts on this stuff, and maybe they'll join us in a minute.
Yeah. Because like I said, I'd really like to know the answer to this question now that we've gotten.
Yeah. So can we just talk for a second about irreducible representations? Because I'm just trying to understand, because as I understand it, one of the things you're trying to do is find representations of these super Lie algebras.
That's correct.
Right. So what I'm trying to understand is, if we were trying to find out, does our model, does it have some wonderful super Lie algebra that pops out of it, for example?
Yeah.
The question is, how would we know? Because all we see is these things where, I mean, we're making it, from the dust up, so to speak.
Sure. And we are sort of, with Adinkras, also have a very similar philosophy that we're sort of building things from the bottom up.
Okay. That sounds very interesting. I mean, so maybe we should hear about what Adinkras are and how they work.
Okay, well, if you'll turn the screen back over to me.
Okay, go ahead.
I'll get my second
you have control. Go for it.
My second Wolfram, let's see, screen share, desktop. Now, because I prepared a bunch of PowerPoints.
Oh, great. Okay.
For us to go through. I think I just went through the first one. Yep.
Oh, wow.
And
okay.
so
all right.
now, okay, so here's the second one.
I see. I figured the first one was the only one, so I was.
Why would you think that, Stephen?
Okay. Oh, this looks very interesting. These are graphs.
I don't know if it'd be interesting, but let me take you through it, and then you can tell me whether it makes any bells for you. Okay.
Oh, actually, one person on our live stream, Richard, is pointing out that fractional dimensional vector spaces are fusion categories in category theory.
Right. That's the Deligne tensor category thing. So fusion categories are the particular class of symmetric monoidal categories that correspond to Deligne tensor categories. And they're the ones on which you can define this fractional Frobenius-Perron dimension.
Okay, so whoever this person is, do they know the answer to what would happen if we use fractional derivatives to replace the normal derivatives and the generators of SO?
I think they have different I'm guessing that their expertise is different, but hopefully we're finding our local fractional derivative expert.
Okay.
Hello, Michael.
Can I also put my 5 cents?
Go ahead.
That could be totally crazy, but representation of SON are Wigner matrices.
Yep.
So, right, I just typed also in Mathematica, you have
Wigner D. Yes, Wigner D.
Wigner D, right? So, but you're looking at non-integer S, yeah, right? Which is a little strange for D matrices, but D matrices are also about spin, right?
Yes.
Yeah, spin 1/2. So, and here, well, I'm
actually, you give me an idea, okay? Because we know that, for example, the 3J symbols can be represented in terms of hypergeometric functions.
Right.
And so my question then would be, okay, what are the Wigner D matrices in terms of what are those in terms of mathematical, other mathematical functions? Actually, Michael, you might know the answer to that.
There's also some PFQs.
They're PFQs?
Yeah.
And do you imagine, so what then one might guess is that the P in the PFQ has something to do with the D of the SOD, so to speak. In other words, if we were to look at SO2, otherwise known as U1, what will be the analog of the Wigner D matrices, and how would they be represented in terms of hypergeometric functions? That's a Michael.
I think this has been done. There is this Russian, a big clean book from the Russians from 2005. I think they have all of this.
So Michael, this is Jim Gates. Do you know the answer to my question that I posed a few moments ago?
Sorry, unfortunately, when one joins late, one does not see earlier questions, so I don't know the question.
Okay, so the question is, let's start. So I'm trying to understand this whole fractional dimension thing that Stephen has been talking about in the constructions. And so the question is the following. Suppose that I just consider, let's say SO3, because it's a very simple group to consider.
Yep.
I know how to write down vector fields for the 3 generators of SO3. We all know these expressions. If I replace the partial derivatives in those expressions by fractional derivatives, what do I get out when I try to calculate commutators? That's the question. And I'm not trying to put you on the spot. If you have never seen this before, this is something go away to think about. But I'm curious to know the answer to the questions now that I've posed it.
I have never thought about doing this.
Ah, okay.
So Michael, say a little bit about, and I don't know that Oleg is here also, but can you say a little bit about fractional derivatives and how to think about them in terms of I mean, there's an integral transform that defines these fractional derivatives, if I remember
exactly. Correctly. I mean, there are various ways. I think for a physicist, in my opinion, the nicest representation of a fractional derivative is via Fourier transform, because derivatives become multiplication in Fourier space. So normal one multiplication by p, Laplace p squared. So you just basically multiply by something fractional, p to the 3/2, and then define it through the inverse Fourier transform.
So let's think about that, the Fourier approach, thinking about that in terms of what Jim is talking about with these commutators. What would happen if you just take the Fourier transform of the commutator expression and then try and reconstruct it backwards? Now,
but the Fourier transform of a product would become a convolution, which is not unexpected because only integer order of differential operators are local. Non-integer orders are non-local, so you need they basically touch the function far away.
Okay, so what you're saying is that when we're looking at a commutator here, x dot d, things like that, that in integer dimensions, that corresponds to a local operation on the function. Jim, I think this is a highly relevant point here.
Okay, well, I'm glad, I'm just the local mathematical ditch digger in this game, okay?
but listen, I think Michael is making a really good point here. So
like I said, if no one knows the answer,
no, I think we have a partial answer here. I think okay. So the point that Michael is making is that, first of all, think about the fractional derivative by taking Fourier transform, multiplying by some fractional power, taking the inverse Fourier transform. Now, the point is, there is a big difference between taking those Fourier transforms for the integer dimension, for the ordinary derivative and this fractional derivative, because basically in any integer dimension, that's a local operation in
position space.
In position space. But in a fractional dimension, it is not a local operation in position space.
Okay.
And kind of the physics example that comes to mind that isn't quite a fractional derivative, but nearly, is the relativistic case square root of p squared plus m squared. Because there we know from Wigner, Newton-Wigner, Bethe-Salpeter, and so on, that basically we have to solve integral equations for if we take relativistic energy relations.
Okay. Okay. So you guys.
Okay. So we don't have a full answer to this, but
you have part of an answer.
We have part of an answer, which is good.
Okay. So
okay. Now you've gotten me excited.
Well, now I've posed the homework problem for your geniuses, Stephen.
Yeah, right. Well, okay, but you've also gotten me excited about, I think it was Boris's comment got me excited about the analytic continuation of the Wigner D function.
Yeah.
Okay, let's go back. I want to know what all these pictures are in Adinkras. So
okay, so finally back to Adinkras. So here we go.
Yeah, right.
So remember, I was claiming that I'm really trying to, it's a representation theory problem that I'm after, that most of our colleagues have forgotten exists and they don't think it's important. Whereas, so in the 90s, I started thinking about this with one of my students.
Wait a second. So Ceresis on our chat here has said that they can answer this question. They've explored it in great depth. Short answer, you can use Adinkras as encoded dimensional precipitants of the fractional dimensional derivative convergences. I don't understand all those words.
I don't understand either. But my postdoc said that the fermionic directions in superspace are representatives of those fractional coordinates, at least for one specific value, namely 1/2.
That's interesting. Okay, yeah, I mean the half would be, that half is going to end up being, because of it's a Z2 thing.
Exactly, and that's why his comment is also relevant. So
right,
okay, so back to the representation theory problem.
Yes,
so I'm going to start in a very bizarre and weird place by pointing out something that everybody learned when they were in kindergarten, namely that hypercubes exist in arbitrary dimensions.
Indeed.
And so here's the sequence. The first hypercube is actually a line segment. You move it, you move it horizontally, it generates a square. You take the square, you lift it up in 3 dimensions, and that forms a cube. And this sequence of operation goes on forever. So that's the first thing that actually turns out to be an important mathematical observation for supersymmetry and Adinkras. Let me move to the next stage. So let me just concentrate on the 2 cube. Here it is. So if we're going to make a supersymmetric representation, the first thing that we do is we decorate the cube by putting little, you can call them nodes or balls, little black and white balls around the vertices of the square, but in an alternating pattern. Ultimately, these white and black balls are going to be fermions and bosons, where the white balls are bosons and the black balls are fermions. The next thing we do is that we color parallel lines the same color. This induces from the cube a set of equivalence classes. Next, we have a strange rule that says, put an odd number of dashings on every square face in the figure that you're working from. And then I can take the object that it results. I can do 2 things to it. I can hold this vertex that I'm pointing to with my cursor fixed and let it hang under the influence of gravity, and it gives me this. Or I can hold this side of the object fixed and give the other side a twist, in which case it gives me this object. The 2 objects you see on the far right-hand side are Adinkras.
Hold on. Those are just, I'm not very good at detangling graphs in my head. Are those the same graph, just rendered differently, or are they different graphs?
They are different graphs because in order to get, one thing I hadn't talked about is that they're different if you put enough information on them. Let me put it that way.
Okay, so the labels are different, but the structure of the graphs is the same or not? Yes.
No, structure of graphs is different. And in a moment, I'll explain what the significance is. So this is how you build Adinkras, essentially. You start with hypercubes in arbitrary dimensions. In fact, let me just go to that arbitrary. So let me go through the 3 cube. Start with 3 cube. Each vertex gets a white or black ball in alternating manner. Every parallel line gets the same color. On every square face, there must be an odd number of dashings. So
wait a minute. So this is a coloring. So effectively, you're saying, given any node, the node in n dimensions, the node has n neighbors.
For the simplest class of Adinkras, that's a true statement. It's irregular, as my graph theorist friends tell me.
Okay, so then in that case, from a given node that's white, every one of the n nodes that it is a neighbor of is black. Is that correct?
That is correct. It's a bipartite graph.
Okay, and it's obvious you can do that. Yes, it is obvious. So for this type of graph, it's obvious you can do that.
Yeah, what's not so non-trivial is to prove that you can do this in arbitrary numbers of dimensions. But the answer turns out you can.
Right. So in other words, it's bipartite. Any n cube, n hypercube, is
automatically admits a decoration of its vertices that's bipartite. Like
okay, and so in terms of this coloring, I'm still just trying to understand that. So you seem to have every bosonic node here seems to have salt. No, it doesn't. I'm now confused. I don't understand where the dashed and colored lines are coming from.
Okay, so let me back up a moment, because this is like in the guts of Adinkras. So to the left of this image, we see a cube with its vertices fully decorated.
Mm-hmm.
Now, to the right, what we have done is every parallel line gets the same color.
Okay.
And so what we're doing is defining a set of equivalence classes on the lines that connect the vertices. And there are 3 classes here: red, green, and black.
Okay, fine. So every in the d-dimensional, the things oriented in dimension n or k out of the d dimensions, it's green for dimension 1, it's red for dimension 2, et cetera, et cetera.
That is correct.
Okay. Okay.
And you can play this game in arbitrary dimensions. That's the important.
Obviously, right. With in d dimensions, you have d colors.
That's correct.
Okay.
Okay, so the next step is the dashing rule. So let's go back. Here there's no dashings.
Mm-hmm.
The dashing rule says every square face must have an odd number of dashings. So you can see that's satisfied on the bottom. It's satisfied as we go on the top, the left, and the right.
Okay.
Where each of those faces has 1 dashings, but the front face has to have then 3.
Right. So I mean I don't know why you're putting that constraint, but I'm assuming
I'm gonna explain that in a moment.
Okay.
So and then the final point is that there's a kind of an index that has to be assigned to each vertex. We call that index height. And so one way to get a consistent height here is imagine this is a real object, fix this node and let it hang under the influence of gravity. That will take you to an object that looks like this.
Mm-hmm.
And now you can see that the white nodes, 1 here, the 3 in the middle, are all at 2 different heights, and the black nodes are at heights that are not the same as the white nodes.
So
now,
just so I understand, this hanging under gravity, if I just look at it in terms of graph distance.
Yes.
So
yes. Your answer to your question is yes, Stephen.
Okay, so it is basically graph distance.
That's correct.
Okay. All right.
Okay. So
your version, I mean, okay, this is why you see part of the origin of this discussion was that we had a discussion with Andy Strominger and some of his graduate students, one of whom is your daughter.
Yes, I know.
and she said, and this is something one always hopes one's children are going to do. She said, my dad has a theory that might be relevant to this.
Okay. She's my agent. I have to give her a commission now.
Yeah, right. Okay, keep going. Yes.
Okay. So the object to the far right here is an Adinkra.
Okay.
Let me go through one more example. Oh, I'm sorry. Adinkras encode matrices. And that's part of the reason why the coloring is important.
Okay.
So if we decompose the Adinkra into nodes that are only connected by black lines, or nodes that are only connected by red lines, or nodes that are only connected by green lines, we can use these figures, we can map those onto matrices. This says the 1 vertex is connected to the 1, the 2 is the 2, the 3 to 3, the 4 to the 4. Well, that's the 4x4 identity matrix.
Wait a minute. You're looking at the adjacency matrix here.
That's correct. That's correct. Okay. And
so
now, if I
so you're taking the subgraph that corresponds to a particular color of edges.
Correct.
You're looking at the adjacency matrix associated with that subgraph.
Correct.
Okay.
And now I can explain the dashings. So
Okay.
let's do this in red, which is on the next line.
Yep.
So if you look in red, you see that you get these figures. This says the first node is connected to the second, but the second node is connected back to the first.
And that's going to be an I or something in your adjacency.
It's a minus sign. You anticipated, Stephen. It's a minus sign.
Okay.
And same thing, 3, 4, 4, 3. I don't know if you use this tensor notation, but this is a way of writing a 4x4 matrix.
Yep.
Okay, and then the green turns out to be this. So
that's a Pauli matrix. The sigma is a Pauli matrix.
The sigma is a Pauli matrix. The identity is 2x2 identity.
Mm-hmm.
Okay. So Adinkras have the really interesting property that they lead you to Clifford algebras, basically.
Okay.
And so here's the game in 4 dimension and with the 4 cube.
Mm-hmm. Okay, so that's essentially that thing down there reminds me of a Hasse diagram.
That's right. That it is in fact the Hasse diagram.
Okay.
Okay. So I'm now introduced you to the basics of Adinkras, namely that start with the hypercube, do this adjusting the vertices, decorating the vertices, decorating the links according to these rules, and then the final rule is that you want to, as you said, you want to look at the graph distance between vertices, and you put some rules there. And when you enforce them all, you get Adinkras. And it turns out that when you do that, you find solutions to that one-dimensional version of the problem that I couldn't solve with John Schwartz.
Okay, so I'm still just trying to ingest this for a moment. So
no problem, take your time.
You're saying that, so first of all, there's a unique bipartite, there's a unique way up to black-white exchange to color the original hypergraph, the hypercube.
I would have said there are equivalence classes of doing that because, color is just some kind of placeholder in our mind for the definition of equivalence classes. You could have used any colors, right?
No, I understand that, but I'm saying that in terms of which node gets the fact that what is not immediately obvious to me is that there's a single pattern of coloring the nodes black and white. And this goes back to something I said earlier, that it's not obvious that you can do this. It's the dashing. Look, with a little bit of work, one can prove that the alternating black-white is really simple for hypercubes. What's not so obvious is that you can put in the rule that every square face has to have an odd number of dashings. That's the one that you have to work a little bit for. Mm-hmm. Okay. All right.
Okay. So, as I said, so as you mentioned, Stephen, these are basically adjacency matrices, and here you would have to have 4 different adjacency matrices, one associated with each color.
Mm-hmm.
And now let me go back to the problem that I was first showing you. Where did I put it?
So I'm sorry, there's an interpretation then of these things in terms of those the representations of this super Lie algebra. Is that?
That is correct. That's exactly right.
Okay.
Because by that means that I just showed you, which just starts from a bunch of geometrical dressings of graphs. If I look at the adjacency graphs, I find solutions to the set of equations you see at the bottom.
But so what is the family? I mean, so given a Lie group, there's a presumably infinite family of irreducible representations of that.
That's correct also.
So now how do you get, is it what sequence of Adinkras give you that sequence of irreducible representations?
We don't know the answer to that question.
Okay, fair enough.
What we can tell you is that we know how to find what the construct that I just showed you leads to the minimal, for any given color, it leads to the minimal representation for any fixed number of colors. But we don't yet have a theorem or a way to classify the higher members of these irreducible families. Okay,
so just so I understand, if I want to make, being naive, if I look at like a rotation group, some very simple thing with simple that could be defined by a simple set of commutators and things like that.
Yes.
Are there Adinkras that correspond to the rotation group?
Yeah, well, in a sense, yes, because if you put a, I'm sorry, let me, hang on a second. Let me see if I can remember where to find this. Let me show you one other thing. Let me say it this way, Stephen. Suppose I put minus signs here.
Mm-hmm.
Then you have objects that effectively are the orbital angular momentum, are the spinor representations of orbital angular momentum.
Yep.
And so, yes, they sort of know, I mean, this construct naturally leads you to double covers, well, it leads you to Clifford algebras and ultimately to rotation algebras, always.
So just at a naive level, I mean, if you took your Adinkra-like construction, I mean, so there were all these things, I mean, I don't really remember them very well. In fact, you know, with Young tableau and things like this for
Yep.
you know, constructing the irreducible representations.
Yes, sir.
And so is your Adinkra formalism, I mean, can you map some of those things into your Adinkra formalism? And is there a way, like, for example, instead of taking black and white, you know, nodes, you just have one color of nodes and different rules and so on? Do you?
So, Stephen, the question is a good one. We don't know the answer because, remember, I specifically set out to study supersymmetry, and there are only two classes of particles in supersymmetries, namely fermions and bosons. So I must look at graphs that are bipartite to represent that.
Okay. So maybe you should explain, because the relationship to Clifford algebras. So.
Oh, okay, sure. Hang on a second. I'm going to have to.
But so I mean, what I'd be curious about from your, which is sort of perhaps relevant both to your kind of thing and our kind of thing, is, you know, is there a nice graph theoretic, you know, interpretation of representations of arbitrary Lie groups?
I would say the closest that I know to that are the weight spaces that you know just as well as I do. Those are sort of graphs.
Yeah, I mean, I don't. Yes, I mean, my knowledge of them is pretty decayed at this point. But I mean, there's also a thing that I don't really understand very well. Maybe you've studied. My friend Predrag Svetanovich has his whole.
Oh yeah, yeah. I visited him sometime last year or the year or two ago.
Right. I've known him even longer than I've known you. So
okay.
But I don't understand. I mean, it took him like 30 years or something to write his book about bird tracks and Lie groups.
Right. Yeah. I have a copy of that book in my computer.
Do you know whether there's a relationship between what he's doing and what you're doing?
Well, part of the reason I don't know, but you know, I went. Part of the reason I went and met him was to talk about that very question. We walked away not knowing the answer.
Okay, fair enough. Okay.
This doesn't show it so well, but the point is that our L and R matrices. So start with a Clifford algebra in a Euclidean space. That's what number 12 tells us.
Yep.
If you start with the Clifford algebra in the Euclidean space, then you can always take one of those Clifford elements and use it to define projection operators with respect to the remaining n.
Mm-hmm.
Then you can, once you have these projection operators, you can act on the remaining n elements in the Clifford algebra, and that generates these things called L and R that we see here. But these L's and R's are exactly the things that I get from the graphical construction. So this is
how. Let me just try to understand this. So I mean, the Clifford algebras, normally you would have what, 2 to the n dimensional. I mean, you know, there's a what's the relationship? So first of all, a d-dimensional Adinkra. What is the d in the d-dimensional Adinkra? What does that d correspond to?
The d in the d-dimensional in Adinkras actually corresponds to the number of bosons or fermions in a supersymmetric representation.
So as I look at like the supersymmetric analog of some particular well, what's the simplest one of these what's the simplest example where there's of a supersymmetric
the simplest non-trivial one I'm about to put up in front of you, it's this. Namely, this is the simplest non-trivial Adinkras.
Yep.
And I've decomposed it into its different colors, which leads to these adjacency matrices. And you use these adjacency matrices in the formula that I showed you for the realization of the supercharge, which was that I said you have to do what's on this image. Namely, when you say the supercharge acts on a boson, it gives you this L matrix. When the supercharge acts on a fermion, it gives you this matrix, but times a spatial, here space only has one direction, the spatial derivative acting on the boson.
So down below your anti-commutators, what's the interpretation of those anti-commutators in graph theoretic terms?
That's, oh, by the way, that's what all those plus and minus signs are about, by the way. It's the minus signs that enforce those conditions, that the dashing. Remember I had
no, I get it, but I'm just, I guess I'm asking, if you take, you know, L dot R effectively, you've got a product of two adjacency matrices.
Correct.
That's correspond to the two-step, you know, that's, you know, the product of those adjacency matrices is like you go first on an L edge and then on an R edge.
That's correct.
Okay.
So if you take the trip in one way, if I can call the motion a trip, you take it, so you take a plaquette, you pick color 1, color 2. It takes you from one place in the representation space to another place. Now do the same thing, but choosing the colors of the links in the opposite order. When you add those two things together, that's what these two equations on the bottom.
Okay, so to what extent is this like curvature in that space?
It is almost like curvature, except that the sign is wrong.
Okay, but now in the case where you're not dealing with the super example, the sign probably is, you know, if you didn't have the super business, you would have commutators, not anti-commutators.
That is correct.
So in what sense then is is this thing the analog of, so you're saying in this Adinkras space, so to speak, the presence of these commutators, it's saying that there's a certain amount of curvature, but not, well, I'm not sure whether it's saying this, maybe it's saying there's zero curvature, I'm not sure.
The closest analog would be zero curvature, but non-trivial torsion.
Right. Yeah, in fact, it's an interesting thing. In our, actually, there's a question for Jonathan here. Do we end up getting torsion in any of our metrics? Or are we forcing it not to have torsion?
Yeah, so the construction of our spacetime metric assumes torsion freeness, but that doesn't necessarily hold. And yeah, that's a really interesting point. That an interpretation is that curvature in supersymmetry becomes effectively torsion. I hadn't thought about it that way before.
Yeah.
So wait, what are you saying? You're saying curvature in, but these are small discrete spaces. But one could imagine in a bigger Adinkras, so to speak, that the thing would be closer to a continuum limit of curvature. Or is that not correct? I mean, in other words, if I were to take, instead of a one move L and R matrix, I was to take a multi-move, you know, if I was to take multiple moves through this Adinkras graph, what would that correspond to? I mean, that's, I'm just trying to.
No, you're asking the right question, Jonathan. I'm sorry, Stephen, and that I don't have good. We've actually done some. That's part of what this whole notion about holorome. You asked me about this funny word that you've never seen before. It's precisely this point: is that if I try to take the conventional definition of how I measure curvature, I would want minus signs between these objects, not plus signs.
Exactly.
And when you do that, you do get matrices out on the other side that, roughly speaking, are kind of like curvature. So that's what the holorome was all about.
I see. So, okay, but coming back then, okay, so back to your Adinkras. So you're saying, I mean, the problem you're trying to solve, and the thing you were talking about with n equals 11 supergravity and all this kind of thing.
Which, by the way, n equals 11 supergravity corresponds to 32 colors.
Okay. So the colors are indices of generators, is that right?
That's correct.
Okay. And each vertex, do you have separate vertices for the time and space derivatives, or does a white vertex or a black vertex also contain time and space derivatives?
I'm sorry, that is you speaking, right, Jonathan?
Yes, yeah. Sorry, we should ID ourselves.
Yeah, and the answer to your question is when we do the higher dimensional versions of Adinkras, yes, the nodes are in fact functions of space and time.
Okay, but both the fermionic and bosonic ones, or just the
both?
Okay, interesting.
I'm very glad that Jonathan and I can be mixed up because Jonathan is very much younger than I am, and so that's
well, Stephen, my students who are on this call with us will tell you that I often mention to people that I have a single active brain cell remaining.
Oh yeah, that's I don't know. Then it must be doing very well.
You're doing better than most of us.
Well, my claim is it dupes us because the input-output rates are fantastic.
But so actually, we had a number of questions here on the live stream. So
okay.
The question here: does the coloring correspond to grading in the Coffin algebra?
No, unfortunately not. The grading comes from the dashing rule.
Okay.
Oh, really?
Yeah, that's where the.
Okay. Because I was going to ask when Stephen mentioned before about this, these things looking like Hasse diagrams, right? So
but this is just one example, and it's kind of an accent here. But I'm very familiar with this appearance of looking like a Hasse diagram.
Okay, but so that doesn't happen in the higher dimensional cases, is that right?
Not necessarily.
But when you get this partial order, does that not give you? I mean, does that not give you some notion of grading? The height of a vertex, or am I completely confused?
No. That is one grading. That's what physicists call engineering dimension. That's a ZN grading.
Right. Okay. Yes, that's what I was trying to. Okay, I understand.
But the Fermi-Bose grading is the coloring white or black of the nodes.
Yeah, it's confusing that we have two radically different notions of grading going on.
Okay. Yeah. And there are in the Adinkras there too. There's the integral grading, which is the height of a node in one of these diagrams, and then there's whether the node is black or white, which corresponds to fermion boson. So it's a Z2 there.
That makes sense.
So the thing that you've recently solved is to be able to deal with this 32-dimensional.
Yes, in fact, my students who are on the call, both I think Hazel, are you here, Hazel?
Yes, I'm here. Younger is also here.
Younger, okay, so these are my two graduate students.
Hello there.
Stephen.
Hello.
And for just over a year, we've been making breakthroughs that allow us to. So far in the discussion, I've only concentrated on Adinkras with one dimension because it turns out they are fascinating. They have a ton of mathematics, and I think my colleague Kevin Iga is also on stream with us. And Kevin has actually written a book for mathematicians. Well, it's not quite finished, but it's now at publishers. But it's a book on for mathematicians about exactly what are Adinkras. I would recommend that if it ever goes to get published, that you and Jonathan and your folks there might be interested in looking at it to get some.
Actually, just out of curiosity, if somebody can say what. Are there mathematical buzz terms that connect to things like these Deligne categories and so on that come out of Adinkras?
So Kevin, if you're online, can you speak to us?
Don't have him. Okay. Well, okay, no matter.
Yeah, but he's the folks that I regularly collaborate with. He is the guy that I would put the question to.
Fair enough. So, but okay. So you were about to explain the adventure of n equals 11 and so on.
Well, yes, and for that purpose, so in one dimension, I showed you the rules for constructing these things. In 11 dimensions, anything greater than 3 dimensions, the rules actually become rather different and more interesting. And so for the last year, a little over a year, I and my graduate students, Yang-Rui and Hazel. Hazel is my student. She's Hazel, you're in your third year or fourth year?
Fourth year.
Fourth year for Hazel. And Yang-Rui, you're in your third year?
Yes.
Okay, so these are my fourth year and third year students. For the last year or so, we've actually been figuring out how do you construct Adinkras if there is more than one space-time direction? And the answer turns out to be a rather interesting adventure. And so I'd like to actually, if they're not too shy, I'd like to ask one of them to sort of take us through this part of the story. And I'll quit sharing here, and maybe one of them can share screen or something.
Who wants to share?
Uh,
Hazel, there we go. Terrific.
Okay. So this is an Adinkra in 10 dimensions, the sort of the most basic Adinkra that you can construct.
So let me try to understand that. So this is essentially just a summary of the Adinkra hanging from one node.
Absolutely.
Yeah, and so that's telling you that oh, there we go. Okay. There we go. All right. Okay, so that's telling you the multiplicity. Those numbers are the multiplicity of nodes of that type. What are the two different? When you see two different nodes or three different node types at a given level, what do those correspond to?
So one of my students is supposed to answer that.
Yes. Hi, I'm Yang Rui. I'm Jim's graduate student. I'm in my third year PhD. First, I want to start with this screenshot.
Okay.
This equation is one of the main results in our latest paper published in JHAP. And this paper is about the superfield component decompositions in 10D superspace. So now we are working on 10 dimensions. And in 10D superspace, since the Majorana wild spinner has 16 real components, so if we do a theta expansion for a general superfield, we can get 0th order until 16th order. That's why.
Sorry, what expansion? I just did, there was one word I didn't hear there.
Theta expansion. Theta is a Grassmann coordinate in superspace.
Oh, okay, theta expansion. Okay, so I need to try to understand that. So you're saying that you're taking, actually that part I don't quite understand.
Okay, so in superspace, we extend our space-time. So we not only have the space-time coordinate, we also have the Grassmann coordinate to represent some fermionic properties.
So this is a scalar superfield.
Yes, the V is a scalar superfield.
Yeah, and the level 0 to level 16 correspond to the expansion of superfields.
So can you put up a picture for Stephen and Jonathan and his colleagues, a picture of the superfield itself, as opposed to just talking about this representation? You know, phi of or V of X and theta. Do you have it somewhere convenient?
By the way, various people, let me just respond to a couple of things on our live stream here. Various people are asking about all sorts of different things here.
Okay.
So first of all, somebody was asking about torsion, and torsion is supposed to be 0 in general relativity. Yes, ordinary general relativity has 0 torsion.
But you're correct, Stephen, but supergravity never has 0 torsion.
Ah, okay. In the metric of supergravity.
It's not the metric. The torsion shows up because of the connection. You don't use a minimal connection in supergravity. You don't use the Christoffel symbols to define the connection in supergravity.
Oh, and so I see. So the torsion is showing up because of a difference. Usually the Christoffel symbols have a certain symmetry which they don't have in supergravity.
That's correct, because in supergravity you let the so-called gravitino generate the torsion.
So let me understand that. So you're taking a covariant derivative, and normally that would just extrude Christoffel symbols, so to speak.
That's correct.
And what you're saying is that those Christoffel symbols usually would be, you could interpret as being parts of the gravitational field.
That's correct.
You're saying in addition you have a gravitino field. For
supergravity, yes.
And that the gravitino field, so what does it mean that there's non-zero torsion? What does that? I mean, it means that the metric tensor is not symmetric.
Okay, so the role of the connection is to tell you how to define differentiation on the manifold.
Yep.
But that means that there are different definitions of differentiation depending on your choice of the connection. And so you can make a choice where it's dependent on the gravitino, which is different from the choice when it's not dependent on the gravitino. And supergravity always makes a choice to have it depend on gravity.
So asking on the live stream, how does torsion show up in physics? What are the physical implications of torsion? I think it's that well, maybe somebody else can explain. I mean, the immediate thing is the metric tensor G mu nu is not symmetrical in mu and nu.
Well, that's one way to say it. The way I sort of, so if someone gave you a gravitationally covariant derivative, since for the people on this discussion, at no point have we introduced the gravitational covariant derivative, so let's be clear about that. When we talk about the alpha, those are not gravitationally covariant derivatives. Those are operators who are analogs of the Gelman matrices. I tried to make that clear. But in general, if someone gave me a gravitationally covariant derivative, I could calculate its commutator.
Yep.
If the Christoffel connection is used, I know that when I do that calculation, all I get is curvature.
Yes.
However, if you use a connection that's different from the Christoffel connection and carry out that same calculation, you will find that the right-hand side of the equation includes a term that is linear in the derivative operator that you're using. The coefficient of that is the torsion.
Okay, so you're saying normally when I take covariant derivatives and I take the commutator, I'll just get a bunch of Riemann tensors and things out on the other side.
Correct.
That's just the curvature. And you're saying in the case where there is torsion, I get out something which is linearly proportional to the original derivative operator.
That's correct.
And so what is the physical interpretation? So, I mean, if you have a torsion, I'm trying to remember, there are generalizations of Einstein's equations that have torsion.
Okay, so if you think of it in terms of geometry, let's do that first. When you calculate the commutator, what you're doing is calculating an infinitesimal, an infinitesimal trip around a quadrilateral in two different ways, and then asking what's the difference.
Yep.
Right? And the difference turns out to be, if you had a vector, it gets rotated.
Yep.
And those rotation coefficients are the Riemann curvature tensor.
Mm-hmm.
If there's torsion in addition to that rotation, the vector field is also subjected to an additional translation. And the torsion is a measure of that additional translation.
Oh, I see. And so in are there generalizations of, this is general knowledge question, but I mean, are there, I have a vague recollection that there are generalizations of Einsteinian gravity that have torsion and then give different properties with respect to, I don't know, black holes or whatever else.
I don't.
Is that right?
Certainly, in principle, yes. I don't remember the details either, since I'm not a
Right. My understanding is that you get this additional tensor structure that occurs basically because you get a Lie bracket of vector fields appearing because of this additional vector transformation that Jim mentioned.
Yep.
And is there any serious theory that has torsion?
Oh, there are lots of discussions of torsions in cosmology and astrophysics. It's a perennial discussion.
Okay, fair enough. Fair enough. Okay, let's go back. I'm sorry, Yangri was okay. So she was showing here. This is an expansion of what is V?
Yes, the equation 4.1 is the general scalar superfield in 10D unequivalent superspace.
Okay, so this is an expansion in small theta of the value of V. Is that right?
That's correct.
Yes.
Okay. And so these thetas are Grassmann variables. Is that
correct?
Right. Yeah.
Okay. So in principle, when you get to the why isn't there a theta beta theta alpha that is not the same as theta alpha theta, or am I mistaken?
That's because in 10D, we have the if you consider the Clifford algebra, and we have the Majorana-Weil condition for the spinor. That means the Majorana-Weil spinor has the 16 real components. Not like in one dimension, we just have one theta. But in 10 dimension, we have 16 different theta.
I guess the question I'm asking is, maybe I'm being silly here, but given that the thetas do not commute, these are non-commuting quantities, correct?
Anti-commuting.
Anti-commuting.
I see.
So for a specified theta, it cannot be squared.
No, I get that. Right.
Yeah.
Okay, fine. I understand. All right. So okay. All right. So this is an expansion there. So now.
Yeah. That's why we can only have the level 16. We just the theta 1 to theta 16.
Because the wedge product, I don't actually understand why there are wedge products inside these different levels. Are those wedge products in the sense of p-form wedge products?
Yes, they are. The
Yes.
point is that the Grassmann variable itself is anti-commuting. It's not that it's non-commuting, it's anti-commuting.
Yeah, I get it.
And because of its anti-commuting, it means whenever you write two of them, they're automatically forming a wedge product.
Okay.
Or if you three, it would be the three wedge. You know, so it's the anti-community of the Grassmann coordinate that induces the wedge product.
And so wait a minute. So these different levels, what does it mean? So you've got okay. The 16 is like, those are the components of the original spinner type thing. And then you're forming at these different levels. Okay, I'm a little bit lost here. What?
The 16 is the, okay. So now we are working on the Lorentz group, right?
Mm-hmm.
The 16 is the spinor representation for the Lorentz group SO1,9 because we're in 10D.
Yep.
Yep. And now in equation 4.2, we are using the wedge product to count the total degree of freedom at each level.
Yes, I understand. But these levels correspond, I mean, should these levels be thought of as, I mean, okay, naively, I got a bunch of spinners. You know, maybe
Yes.
they're, you know, maybe physically, you know, make it up electrons or something. And now I could imagine having combined object, or quarks, let's say, you know, combined objects that have, let's say, you know, 5 quarks all together, and I have something which is the, you know, I'm asking what are the what are the combined sort of generalized spins that you can get? Is that how I should think about these different levels, or what? How should I think about these?
Okay,
levels?
so we can go back to equation 4.1.
Mm-hmm.
So the first term is zeros. We name it the level 0 because there is 0 theta.
Yes.
So the degree of freedom of the phi 0 is just 1.
Yep.
Yep. Okay, look at the second term.
Oh, okay, I get it. So this is just
Yeah.
a representation of this expansion. This is just saying, by level n, you're just saying the nth derivative is this thing that has has n anti-commuting thetas. Each theta has 16 components.
That is correct.
That's
Yes.
right.
Yes.
That's right.
Okay. Okay, I think I understand so far.
Okay. So yeah, for we can calculate. So just like the equation 4.1, the level 1 we have the phi alpha, and level 2 we have phi alpha beta. But this is just most general form.
Yes.
Yes, we need to find out the irreducible decomposition for like the phi alpha beta.
Yep.
Yep. So let me go back to the Mathematica file. All right. So by using some group theory tool, we got finally, this is our final result.
Okay. So this is saying.
And at each level, these numbers represent the dimensionalities of the component fields sitting in this level. And they are also the dimensions of the irreducible representations of SO1,9.
Of the spinor representations.
Okay, hold on. So SO1991, whatever, is, okay, first naive question. Isn't there just one spinor representation of SO19?
Yes.
And its dimension is 16.
There's one basic spinor representation, which is of dimension 16.
16 and 16
There are like
are,
representations for like spins 3/2 or whatever. So
wait a minute. So the spinor is like, and again, I'm not familiar. I'm not as used to working in. Okay, so it's like the spinor is like the spinor half creature in. So let's see. This, you're saying this thing has 16 components. So you're saying it's what is the dimension of a Clifford algebra for d-dimensional space? It's 2 to the d over 2 or something. Is that right?
Something like that. Yeah.
It's something like that, a little bit more complicated, but something like that is true.
Right. So then your 16 here is like a spin-a-half particle. Is that right?
Yes.
Yes.
And so then your further ones up here, is it the case that your blue ones are the bosonic things like spin 1 and then the next one?
Right. Yeah.
Okay. So then, okay, naive question. Okay. So if I were to look at the corresponding thing in 3-dimensional space, would I see there, would this be 1 for level 0, 2 for level 1, 3 for level 2? Is that correct? And then, because level 2 would correspond to a spin 1 particle.
No, that's not correct.
Okay.
For 3-dimensional space, spinners are only 2-component long.
No, I was saying that at level 1, that's your spinner. That's your spinner half.
Right, so
thing.
that would be 2.
Right, and then at level 2, that's your spin 1 object, isn't it?
No, I'm sorry, no. If you consider a spinner for a 3-dimensional space that is only a 2-component object, so it obeys the Pascal's triangle, 1, 2, 1. So when you get to the next level in 3 dimensions, I'm sorry. When you say 3 dimensions, do you mean 3 spatial or do you mean 3 spatial and 1 temporal?
No, I meant, okay, let's try and unconfuse. I was just thinking about ordinary SO31.
Ah, okay.
3-dimensional space.
Yes. So it goes 1, 4, 6, 4, 1. That's a Pascal's triangle.
Wait a second. So your spinner in that case would be a Dirac spinner, or it would be a.
It would be a Majorana-Weyl spinner with 4 components.
Okay.
So 1, 4, 6, 4, 1, and that 6 would decompose into a 1, a 4, and a 1, and the 4 that you're looking for is there. So,
okay,
in other words, Stephen, if you look at what they have on the screen, in 4 dimensions, it reads 1, 4. At the next level, it actually reads 1, 4 plus 1. You see how at level 4 in this diagram there are 2 representations?
Yes.
If you're in 4 dimensions, there would be 3 such representations occurring at level 2.
Okay, and what do those correspond to? Those correspond to, what do those correspond to?
They correspond to fermion bilinears that are antisymmetric, and that means that it's a singlet. It is the axial vector, and it's the gamma 5.
Hold on a second. Hold on. So you're saying you're saying there's a vector. These are the, gosh, this reminds me of weak interaction theory. So this is
that's exactly what it's supposed to remind you of.
Okay, so wait a minute. Back in the day, there used to be this scalar vector, tensor, axial vector, pseudo-scalar.
That's right, Stephen.
Yeah. Okay. That takes me back a long way. Okay. So in your version of this.
Thank you. I don't know which one of you changed it to 4 dimensions, but thank you.
Yes. Okay. So wait a minute. So those are the things I just mentioned. The scalar vector,
right,
tensor.
the fermion bilinears. That's right.
Okay. Oh, they're in a different order here. Okay. So the last one is the gamma 5 one, which is the pseudo-scalar one. The first one is the. Yeah, I get it. Okay, so hold on. Level 1 is just, okay, so they're bilinears, all right, and then you have a trilinear, which I don't know about otherwise. Why do you only have, oh, I see. Those have to be, actually, I'm a little confused here. So at level 2 there, you have, what are those in terms of so that last one looks like it's a pseudo-scalar, the one with the gamma 5.
Yeah, that's right. And
the one before it looks like it's an axial vector, the gamma 5, gamma A.
That's also correct.
Okay, so, and the one before that, what is that C sub AB?
So this is something
that people don't normally
talk about, Stephen, but in superspace, it is useful to introduce the notion of a metric for the spinners.
Okay.
And the object C is that object And the way that you would have studied in the old days, you would have said, I could write psi bar psi as the scalar.
Mm-hmm.
I would have written psi gamma phi gamma mu psi as the axial vector.
Yep.
And I would have written psi bar gamma phi psi as the pseudoscalar.
Yep.
And so those things that you see at level 2 are precisely the same objects with a slight sort of jazz because it's supersymmetry.
Okay, okay, fair enough. Okay, the trilinear thing, would I be familiar with that from that doesn't ring a bell at all, because you don't end up with, in Lagrangians, you don't end up with psi type stuff.
Exactly.
Usually.
And so, but it turns out that if you look at the Lorentz transformation property of the object they're pointing to,
Mm-hmm.
it has exactly the same Lorentz transformation properties as the object at level 1. And that's why it's a 4.
Okay. 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 So the interpretation, I mean, I'm still, is there a space-time interpretation in terms of spins and things of these various numbers? Or is this a different sort of some kind of super property?
No, I mean, these properties were known before supersymmetry, so we can't blame supersymmetry for these things.
No, but I mean, is there an interpretation? Because okay, looping back to the thing that I'm most, focused on here, which is this question of in our models, how do we understand from limits of graphs and things the presence of things like spin? And so I guess I'm curious, what is it, the interpret? I mean, are these internal quantum numbers in the supersymmetric setup, or are these supposed to be space-time quantum numbers?
These are space-time quantum numbers because in supersymmetry, the theta carries the representation of a spinner.
Okay.
So these are not internal quantum numbers; they're space-time numbers.
So if I were to look at just particles that come out of this theory, what spins would those particles have?
That's shown on equation 3.4.
Okay.
The first particle, which is called V0, is a scalar.
Okay.
The second particle, which is called V alpha 1, that's a spinner.
Mm-hmm.
At the next level, there are 3 different particle types. There's another scalar, which is V12. There's a pseudoscalar, which is V22. No, the pseudoscalar, V22. And there's an axial vector, which is VB2.
Yeah. Okay, but what about after that? So those ones I sort of understand. So okay. By axial vector, we mean, takes me back, that means j to the p of 1 plus.
That is correct.
Okay, so then what goes on after that?
So the point is, if you're in supersymmetry, you can't stop there. You have no, how do I say this? There's no justification for stopping the expansion in theta. So you have to keep going until.
Okay, so what's the next one? What is the spin of the next object?
It's spin 1/2. The
3 theta thing has spin 1/2.
Yes, remember I mentioned that it transforms under Lorentz transformation in exactly the same way at level 4 and level 3. So it's got to be spin 1/2.
I see. So there aren't higher spins. So I mean, I vaguely remember that the just in the particle content of supersymmetric theories, that there are a bunch of spin 3/2 particles and things that come out.
Only if you go to a different multiplet.
I see. Okay, so here you've got an additional spin 1/2 particle, and that thing with 4 thetas is what? Is that a spin 0 again, or what?
Yes, it is.
Okay. But that's not the end of the expansion. I would go up to 5 thetas.
No. Yes, it is the end of the expansion because there are only 4 thetas.
Oh, that's right, because it's in 3 dimensions. That's right. The number of, but in 11 dimensions or whatever.
Ah, indeed. That's what they were showing you with that thing going from 1 to 16.
Okay. I'm finally now vaguely understanding. Okay, so that's essentially the particle content of your thing in your n equals 11 case.
Well, I'm sorry, that was 10 dimensions they were showing you, not 11.
Okay, all right, 10-dimensional case. So what's happening? Can we go back to that one? I wanted to see the 10-dimensional thing here. Okay, so are these just alternating between spin 1/2 and, well, I don't know what spin 1/2, spin 0, spin 1?
Well, they're doing the analog of that, but in the higher dimension, yeah.
What do you mean the analog in the higher dimension? I mean, so the spin, I mean, there's still a notion. I mean, this relates again to this SOD for arbitrary D. I mean, do you consider for D equals 10, for example, do you still think of that as, you know, I mean, you're not changing. There's still a very well-defined notion of spin a half, which is the spinor representation of SO10.
Right.
And
yeah, which is
it's just that the number of components is larger.
That's correct. That is correct.
Okay. So your 120 here, what is that at level 2?
That's actually a 3 form. If you wrote it in ordinary field theory language, that's a 3 form.
Okay. Okay. So I mean, the graph theoretic interpretation of this is how do you sort of think about it at sort of a meta level? This is sort of, well, actually no, I'm going to ask a different question. You know, given this collection of numbers, this is a very specific collection of numbers.
Yes, and let me just say,
Yeah.
Stephen, that this set of numbers you can just get by taking the wedge product of 16 in all possible ways.
Okay.
And then decomposing those representations into irreducible representations of SO19. That's where these things come from.
Okay, but so the thing that I'm curious about is if you are given data about these irreducible representations, and you're asked what group do these correspond to, and let's imagine, because you know the specific group SO19, SO18, etc., they'll all have different collections of numbers.
Correct.
But if I were to be very coarse and I were just to throw you a random collection of numbers,
yes,
you would say, oh, that's not a compact Lie group. That doesn't correspond to the right numbers to form a, you know, a nice, whatever, a compact super Lie group or whatever, probably. And so what I'm trying to understand is what would happen? In other words, does there exist an object, a mathematical object, which, given some more arbitrary collection of numbers, is the thing that is the sort of the reconstructed continuous Lie group-like thing that is approximated by, see, I mean, what I'm getting at is what we're going to get out of these models of ours is something which in some continuum limit might approximate a Lie group.
mm-hmm.
But we're not going to get at, you know, it's a discrete object. So, and what I was really curious about with your Adinkras is if I were to kind of, you know, pick it instead of a nice Adinkra graph that comes from a Lie group, if I were to go the other way around, and say, here's a family of progressive, I don't know, pieces of Adinkras or something, and I just, you know, smush them together, and I say, does this family limit to something?
Right. I understand your question, Stephen. I don't know the answer. I mean, it's a great question because essentially you're saying, if someone gives me some data of multiplets and say dimensionalities, how do I recover the groups that these things are parts of? And I don't even know how to think about that yet.
Okay, so actually I have a thought here. So you're, I mean, if actually, let me, could you unshare for a second? And I'll share for a second here. Hold on, let me just,
listen, Stephen, I have a hard stop in about another 20, 25 minutes or so.
Okay.
So I know, I can go. I don't know if other people can stay or not.
Steve, can I make a comment a little bit later?
Yeah, I was just going to ask one thing I'm curious about. Yes, please make a comment. But
I think I for your question, because but I don't want to hold anyone here, so I'll just, it's not about Adinkras, although I get a better idea about Adinkras from this talk, but it's not about it. It's about the spin that you're talking about, the spin representations.
Okay, I have a guess here. So this here is obviously a 4-dimensional cube, hypercube, and we could, we go to 5-dimensional, whatever. Now imagine that I were to modify this a bit, and I'm asking the question: what is the not quite the 4.5-dimensional hypercube? Because these are just graphs. What I have here is just a graph, and so I just have the connectivity data here. So I mean, I could, if I take this, and that's just a And so I guess what I would imagine is that the average coordination number here, I mean, this is exactly the way that we would compute the volume of geodesic balls, is if I change the average coordination number to not be equal to, in this case, what is it, 5 or something. But if that average coordination number is not 5, but is something different, is D, then I think that's the analog. I mean, so in other words, if you ask what is the Adinkras diagram that corresponds to D equals, 7.5, okay, my claim would be that what it will be is a graph that has average coordination number, whatever, 7.5 or whatever. Anyway, that was just my thought.
Yeah, I agree that that's plausible. Can I ask 2 quick questions to Jim about, related to that?
I'm still here.
Yeah. Okay. Sure. So, the first question is very, very simple-minded. It's just that when this construction of Adinkras, the combinatorial construction you showed earlier, to the best of my understanding, this is a special case for one-dimensional super Lie algebras. Is that right?
That was at the beginning of the discussion. Yes.
Yes. Right. So then, when you're doing, for instance, when you're doing these things in the 4-dimensional or the 10-dimensional case, is there some kind of Kaluza-Klein-like reduction that you have to make in order to be able to do the Adinkraic representation?
Yeah. In fact, that's how Jonathan, that's a great question. The answer is yes. Basically, we use a kind of holography that when we first started this, we only start with the 4-dimensional theory, and then we say, what is left of the algebraic structure if the fields only depend on time? And
right.
then that's how the Adinkras emerged.
That makes sense. Okay. So, and does that work in arbitrary dimensions, or is it specific to 4 and 10?
No, it works for arbitrary integer dimension. I've never tried for non-integer.
Fair enough. Okay. And then the dimensionality of the Adinkras is just the number of supersymmetry generators?
That's correct.
So it has nothing to do with the actual dimensionality of the Lie algebra.
That's also correct.
Okay. So relatedly, I wanted to ask this because I think this was related to Stephen's point about coordination numbers, or average coordination numbers. How exactly do I have an Adinkras? How do I go about getting a corresponding super Riemann surface?
Whoa, that's a great question. And the really weird thing is, for a large class of 4-color Adinkras, we know what the answer is, but I'm not the expert on that. My colleague Kevin Iga, if he's still online, I'm sure he'll be happy to talk to you about that.
Okay, yeah, cool. Oh, yeah, he does seem to be.
Oh, he is? He is? Kevin,
he looks like he's on the Zoom call.
Kevin, if you're on, why don't you jump in here?
Okay, yeah. So I'm finally on the right place. Yeah. So this has to do with what you need to do for an Adinkras is, remember all these different colors. What you need to do is you need to order these colors cyclically. So you have different, let's say you have red, green, and blue, and you'd have to put them in an order cyclically, and then you have to fill in the faces where there are made of cycles that have adjacent colors in that cyclic ordering.
Okay.
So, for example, if there's, I don't know if somebody can bring up an Adinkras example.
Yeah, let me unshare, and then somebody with a Adinkras.
Why don't you pick it up, Kevin? Can't you pull up paper or something?
Let me look for a paper that might serve this purpose.
So essentially what you're doing then is you're taking this graph and you're filling in faces in some way.
That's right. So here's the problem. If you fill in all, so what are the faces? Now, if you have an Adinkras, usually what you have by definition is you have these different colored edges, and if we only focus on 2 colors at a time, what you will end up with is, let me pull up I'll just pull up my system. Trying to find a good picture here. Well, I want to keep on talking while I look for a good picture.
Yeah.
So if you just draw, let's see, an Adinkras. Okay, let's see. Here's the book I'm writing. Yeah, so here's an Adinkras. And if you just look at the green and black edges, for example, you see that they form a quadrilateral, a 4-cycle.
Yep.
And this is supposed to be blue. I don't know. I got this color wrong. But if you
this is why, by the way, this is why every diagram I draw is generated by a program.
Ah, there we go.
That's because otherwise I would never get any of them right. Go on,
right.
please.
So if you fill in all of these with two cells, like just fill in a square here, the problem is in general you won't get a surface because you'll have too many squares that share the same edge, for example. So normally in a surface, an edge, an edge is going to be bounded by two different faces.
Yep.
But if you just fill in all of the two different pairs of two colors, you'll end up with too many faces adjacent to each edge. So the idea is you pick an ordering of the colors, like in this case, black, green, blue, orange, and then circle orange back to black. And you only fill in the ones that have adjacent ones. So black, green, you fill in those. Green, blue, you fill in those. Blue, orange, you fill in those. Orange, black, you fill in those. And if you do that, you'll end up with a surface. And more than that, actually, you end up with what is called, well, it's a graph embedded in a surface, and you end up with what Grothendieck called a descent d'enfant. And,
oh boy, that's really weird. My daughter, who's a math graduate student, is actually happens to be studying those things for a completely different reason right now.
That's awesome. That's great. So,
okay.
Yeah. So this fits into that whole story. These dashed edges, the dashing actually is exactly what is needed to specify the spin structure on these surfaces. In this case, you actually get a torus. In other cases, you'll get other kinds of surfaces. And then there's a whole bunch of work by Simasoni and Rishtikin that relates this to super Riemann surfaces, getting a super structure, like a super manifold structure on this, which is really weird because this is motivated by supersymmetry, but we didn't try to put supersymmetry into the geometry of this, and yet supersymmetry comes out at the other end. So we're still a little bit puzzled as to if that means something deep or if that's just a coincidence.
So let me just understand. So I mean, you've got these Adinkras, which are graphs, and you're filling in faces so that and then these become graphs embedded on surfaces, basically.
That's correct.
And so and you're saying, can you get all kinds of exotic genuses and exotic forms of surfaces from more sophisticated Adinkras?
Sure. Yeah. So I'm not sure what you mean by exotic. I mean, we get a bunch of different surfaces. Yeah, that's exactly right.
But I mean, just labeled by Betty numbers or something. I mean, they're not.
Yes. Oh yeah. I mean, of course. Yeah. So we can of course calculate the genus. You can do that pretty easily because we know how many vertices it has. Of course, it depends on which Adinkra you're looking at, and each vertex has one edge of each color. So depending on how many colors you have, and of course each edge comes from two vertices, so that tells you that. Similarly, the faces are all going to be square faces, so each vertex has n of those, as long as you restrict it to the the cyclic permutation of colors, and each face has 4 edges on it, and so you can write out a formula for. If you know the number of vertices and the number of colors, you can write a formula for the number of edges and number of faces, do the Euler characteristic, and that tells you the genus. So it turns out to be n-4 times 2 to the number of vertices. I think there might be a minus something, something like that. Plus 1.
So the only reason you get a descent d'enfant for a super Riemann surface rather than an ordinary Riemann surface is just because of the sign change induced by the dashing. Is that right?
That's exactly right.
Okay, but so the ordinary Klein classification of Riemann surfaces in terms of descent d'enfant places certain restrictions on ramification type and things like that.
Yeah. So right.
Do those still hold?
Yes. So I guess there's another piece. When I'm saying descent d'enfant, then I'm not talking about a surface only. I'm talking about a surface together with a map from that surface down to the Riemann sphere. And yes, indeed, that does happen. So there is a on the Riemann sphere, you'll have a single boson and a single fermion, and you will have I should say there are sort of two different bases here. The bottom base is just the standard. You got a boson and a fermion connected by a single edge. Mm-hmm. But above that, you have an n-fold ramified cover, basically a z to the n, if z is a complex number, right? Cover of this, where you have one edge of each color connecting the two vertices. So I don't have a picture of this here, but basically imagine a beach ball. You've got a sphere, and you've got a vertex here, and you've got all these different colored edges going between them.
I see what you're saying. Yeah, okay.
Then you have a cover. This thing would be a cover of that.
Right.
You have ramification points in the middle of each of those little wedges of the beach ball.
Kevin,
which presumably
Kevin, shouldn't you just send Jonathan your paper with Chuck and Stephen on this?
Yeah,
please
do that.
Actually, and Kevin, people on our live stream are asking what the title of your book is because they want to know when it comes out.
I haven't figured out the title of the book yet.
Okay.
So we'll.
So you just have to look for your name.
Kevin.
Right.
Kevin, wait a minute. I have a copy of your book and it has a title on it.
It does, but I haven't. I mean, okay, yeah, fine. I'll write. So this is what it is so far, but I don't know. That may or may not change. In introduction to supersymmetry using Adinkras.
Yeah, Kevin. Just the thing you were saying earlier about covering, interpreting these things as covers of the surface is really interesting. So does that mean that you can effectively associate a monodromy group with each Adinkra?
Exactly. Wow.
Okay. And what's the restriction on the monodromy group?
So right. So there are two different versions. There's a version that's just the ordinary monodromy group, which it actually turns out to be okay. So it's just Z2 to some power, but what's interesting is that actually sits inside a bigger Z2 to some higher power, and it's actually better to think of the monodromy group as a code, a linear code.
Yeah, okay.
And the criterion for it to have this dashed, have this criterion where each face has an odd number of dashed edges, that is if and only if that code is doubly even.
So it's a multiplicity 4.
Yes.
Okay. Yeah. That makes sense. Actually,
so that's one version of the monodromy. If there's another version of the monodromy, is what happens if every time you go on a dashed edge, you imagine that you are flipping between two different versions, a positive and a negative. So you have a signed monodromy group, and that is actually a Clifford group.
Right.
That covers the
makes sense.
The code.
So these are linear codes over F2, presumably, for the Adinkra case.
Over F2. Exactly.
So actually, that relates to the question that we asked right at the beginning about power statistics and things. So, you can only define obviously a vector field over a field of a field FP for P being prime.
Right.
Does that not place restrictions on on how you can grade things effectively? Is there something special about the fact about Z2 grading that comes from the fact that 2 is a prime?
Yeah, that's this is these sort of philosophical questions that are,
because presumably if you had a Z3 graded algebra, then this classification would fail, right? Because you wouldn't get a vector.
Right. So Z2 is showing up on all sorts of different places, and they kind of all interlace in this kind of fancy way. So the Z2 is showing up because, of course, you got bosons and fermions.
Right.
It's also showing up because you got solid edges and dashed edges.
Mm-hmm.
And those play around in some kind of nice way. Oh, I should also mention, for those in the audience who know a little bit about differential topology, I will say that there is an analogy, and in fact, it's the surface actually makes it not just an analogy; it actually makes it correct, where the choosing between solid and these bosons and fermions, making a bipartition, is essentially like choosing an orientation, and the solid and dashed edges is similar to choosing a spin structure. And the corresponding thing is, in differential topology, you've got Stiefel-Whitney classes, W1 and W2. And W1 really controls whether or not you have an orientation. And that has to do with whether or not, for each of these things, you have a edge between any two, connects two different statistic particles. And the second Stiefel-Whitney class that governs the spin structures, that has to do with the odd dashing sort of thing. So from my point of view, the Z2 is really a matter of the fact that the characteristic classes for vector bundles really take values in Z mod 2.
Okay, that's fascinating. So that means that the statement that Jim made earlier about the fact that you can construct this by partition is really just saying that when you embed the graph in a surface, the surface has to be orientable.
That's correct.
That's a really cool correspondence.
Yeah.
Yeah. Okay. Well, yeah. Thanks for that.
Sure.
Yeah, that clears things up.
So let's see. I think Jim had to go very soon, and
yes, I do. Unfortunately, Stephen, it's almost 4.
Yeah, this is too much fun.
I agree, it's fun. We need to do this again sometime.
Yeah, right. No, I didn't
even get a chance to. I mean, Jan-Gray and Hazel started to tell you the really cool story where we've been able to use ideas from Adinkras, looking at the low energy limit of M theory, and we're the first people to be able to figure out the 2,147,483,648 degrees of freedom. How do they represent the Lorentz Group? And we got all kinds of cool stuff.
Wait a second. Are you trying to tell me that there are that number of different kinds of particles?
Not states, not particles. The states.
How many particles?
So there are 1,000. Hang on a second. There are 1,000 and 1,494 bosons and 1,186 fermions.
Well, some of those are going to be auxiliary fields, presumably.
A lot
right?
of them are going to be auxiliary fields. That's exactly right.
Okay, so there's not so much work for experimentalists to go and try and track down.
But there's a ton of work for theorists here. I mean, the problem that I was telling you about that I first started trying to solve with John Schwartz is the same problem effectively that I'm trying to now work on with Jan-Gray and Hazel in the context of M theory. Is essentially the problem shows up in lots of different guises. So there's so much work to be done here mathematically, it's ridiculous.
Right, I mean, the contact with the kinds of things we're thinking about, which I don't fully understand, but we have this very simple underlying setup, and we're trying to understand how in the continuum limit certain kinds of things emerge.
Sure.
Like, for example, and I guess the question, well, I don't really.
So let me make a proposal, Stephen.
Yeah.
Since I think, look, the common feature in both of our investigations, at least from my point of view, is graph theory.
Yes.
And so what really might be useful is to try to use our results look, we got a lot of assumptions built in our results because we're only interested in supersymmetry, but to somehow try to use our results on graph theory to see if there, as you said, in a certain limiting case, you can see perhaps our graphs somehow coming out of your work.
Yeah.
Aspects of your graphs. That's the thing that I think is most interesting here.
Right. Well, but I think the sort of the contact point there would probably be this thing about fractional dimensional. I mean, to me, this thing about how do you generalize ordinary Lie groups, because you're using these graphs to somehow illuminate how representations of these groups work.
Correct.
And what I think is going to happen is that your graphs are nice sort of perfect cases where things close because they're interdimensional space. What I'm guessing is that there is that if you're not as perfect as that in some limit you will get you'll get something where in specific cases where it's nice interdimensional space, you'll get what you have, and then you'll get these weird intermediate cases where things don't close properly, but where you can still say as some approximation that you're getting something analogous to some, let's say, fractional dimensional Lie group.
Yeah.
And then, for us, then the question is, can we get, because what we will naturally have is things that are these messy, unclosing kinds of things, which might turn out to have limits that correspond to interdimensional space, or might not. But I think that's the point of contact, is that you're representing things in the question is, can we go from our graphs to something where we understand how to extract something that is like representations of some symmetries of our graphs, and then come and go from what you're doing, where you are going from understood Lie groups, so to speak, to a graphical way of representing representations. Yep. And see whether, that would be the potential correspondence.
Agreed.
Yeah, it's interesting. I think we had. I know you have to go, but I noticed.
I really do. But I said another 5 minutes, and then I got to get out of here.
Okay. I mean, we were. Do we still have questions about fractional derivatives, or did we?
Well, I just hope someone will actually do the calculation that's indicated by my suggestion and give me the answer, because I'm really curious as to what the answer looks like.
All right. Well, I think it looks like we have Oleg, who's even here by video.
Yeah. Oleg and I have been talking in a chat in a sidebar here.
Oh, okay, fine. All right. Well, he's the expert on this stuff. It looks like we're not going to have a chance to see the end of the Hazel and Yangri story.
Yeah. So how often do you do these things, Stephen?
We are doing, well, we don't know yet, because this is actually our very first one. So we're going to be, and the question is, how long can I stay away from my day job and work primarily in physics?
You'll have to answer that one yourself, Steve.
Yeah, right. No, the answer is we're going to do a bunch of these, and it will be great to continue this at some point. I mean, we've been doing sort of live streams of some kind almost every day. But many of them are sort of internal efforts to understand different kinds of things. But I think maybe some of the folks who are on here can separately interact and see whether we can get to sort of the next stage of understanding. I mean, again, I'm sure there is some correspondence between, I just have this gut feeling that there's some way of using representations to sort of approximate. I mean, to somehow form this way of thinking about some approximate generalization. By the way, does anybody on this stream really understand the Deligne categories, fusion categories business? Is that does somebody here really know how that all works?
Kevin, would Chuck be able to do that for us?
Yeah, I would guess Chuck would be the person I would start by asking, but I don't know that for a fact.
Yeah.
Okay, fair enough. I mean, I think because that's the closest case that I've seen of anybody trying to define these fractional dimensional Lie groups. And I mean, maybe, see, the thing is, I mean, and then in terms of the supersymmetry aspect of it, well, we didn't really get a chance to talk about this, but the whole, what is a fermion, what is a boson really?
Right.
And how do we try to understand that?
Yeah.
I mean, for you, you've been living fermions and bosons and putting them in super algebras and so on forever.
That's
but
correct.
For us, we have a pretty definite idea of what they might correspond to in our systems. We could explain that at some point.
By the way, it's worth mentioning that the fusion category story is deeply related to the supersymmetry story, as I'm sure many people here know. Right, that the tensor categories of representations of supergroups are exactly the Deligne categories, and so at some level you can think of these generalized tensor product spaces as being the ones that are spanned by supermultiplets.
So where does the fractional dimensional thing come in there?
Well, like I was saying earlier, from the fact that when you apply this generalized integral functor, you can end up with a Deligne tensor category where your tensor product basically has a non-integer arity.
Well and good, but how does that come out of the supermultiplets?
I don't understand supersymmetry well enough to know the answer. I just know that there's a Tanaka-Krein duality between the tensor product categories and as I say, these spaces spanned by supermultiplets.
Well, so then the question would be for these guys, whether they're, that very long number that Jim was reciting. The question is there an intermediate case where it isn't that very long number, but that would only work if you didn't have, if in the end your space corresponded to something that wasn't one of these nice interdimensional things. Okay, there are many questions. We're not going to have a chance to address more of them here, but it's this was great. You've also done a very important meta thing, which is you've proved that these kinds of discussions can actually work.
Steve, can I make a quick comment? And I know I apologize for holding everybody.
Yeah, go for it.
Was that be sort of similar, like you would have a classical spin, which is not quantized, and then which is not integer, but then you want to somehow obtain an integer representations of that? I've seen something like this. If you imagine an angular momentum, which is classical angular momentum, and it can take any values, right? But then in quantum mechanics, spin only takes certain.
Okay, so we have a guess. I have a guess, at least. Jonathan doesn't yet agree with my guess, but my guess is that in our systems, we think we know what angular momentum is, and we think it has to do with if you take pairs of GD6 from a point that essentially define a plane, you can then, in a graph of any hypergraph, you can effectively define a generalized plane with pairs of GD6 emanating from a single point. Then you can essentially think of angular momentum as being sort of the thing that you get by in terms of edges that span across this plane in some sense. And then so you can think about, if you look at these edges, you can kind of visualize them as something like a vortex of edges in some approximation. It is my guess that there's a relationship between a kind of homotopy associated with the way those edges have to work and the way that one can, and the existence of essentially quantized spins.
Oh yeah, in physics, there are works that consider how you go. It's how you recover spin from semi-classical in a semi-classical limit. So
which part of that? I mean, usually in the semi-classical limit, you're looking at very high spins.
Right. So you and then how you if you want to reduce it to a so it's in a I don't so I would have to collect myself and get a little more, but it's some kind of, I've seen things like you go to Wess-Zumina terms and then you recover the spin 1/2 or spin.
I think the normal thinking about semi-classical limits is that you're really looking at high spins. I mean, that's because whereas what I'm thinking is that the way that essentially it's like, you have a vortex in some vector field or something, and you're asking, there's a discrete, there's a, sort of topological, it's sort of topological discreteness that comes about because in that particular case, you might just have some pi1 of your space, and I'm this is very vague because I don't really know how it works yet.
But I still don't understand.
Quantization or something.
What's that?
It's like a quantization condition, like a Dirac string or something. You can.
Yes, that's right. Like a Dirac string, but it would be a Well, go ahead. Jonathan was about to.
Well, I was just going to say that the thing that still doesn't convince me about this is why, if you're defining quantization of spin in terms of effectively topological obstructions in the causal network, why you don't get quantization of classical angular momentum, because you're not using any features that are peculiar to the multi-way causal network as opposed to the space-time causal network.
Okay,
well,
that's a more complicated issue.
Okay, I'm sorry to interrupt, but I do have to go now.
Yeah, well,
we should let Jim go.
Thanks for joining us, and we should probably wrap this up now and continue another time.
Okay, well, all I can say, Stephen, is the first time I tried to get you interested in your house, was it 10 years ago? 5? I can't remember. We've come a long distance if this discussion continues.
Yeah, right. No. You see, but this is what I mean. I was off physics for quite a while, in case you didn't notice, and I'm now back on physics. So, but also I'm now. This was very helpful in terms of understanding what you guys have been doing, and I think, I am convinced that there's we're operating from two ends of a bridge across a pretty, across this fast moving river, so to speak, and I think
that's what it feels like.
Yeah, I mean, it's non-trivial to fill in the middle of the bridge, but I think it's really interesting. All right, well, we should wrap it up here, and thanks to everybody who's joined this this Zoom session, and thanks to folks on our live stream, and to be continued. And thank you, Jim.
Okay, very good, Stephen. Wonderful to have the conversation, and goodbye to everyone. Thank you for joining us. Let's do this again sometime. It was fun.
Great. Okay, bye.